when we talk about decibels, we're talking about the ratio of power. Okay. Let me give you an example of that. Let's take an amplifier as an example. Let's say it's a power amplifier, a PA stage. PA meaning an abbreviation for power amplifier. Okay. I have an input and an output. I can measure the power going in and I can measure the power coming out, can't I? Assuming I have all the information. So we'll say power in and power out. Okay. Now, when we talk about the gain of an amplifier, this word here, gain, the ratio of output over input. Yes. Now, be very careful with the word gain. There's a technical definition of gain, which you should all be aware of. The word gain means to get something. Now, let me remember when we spoke about amplifiers first time, I mentioned about transformers. Remember, this is a side, this is not part of the notes. Remember in a transformer, I said you could have a transformer something like this, where you could have, say, a step-up transformer, 1 to 2. So I put a signal in here. Let's say the signal is 1 volt peak to peak. What's going to be the signal here? 2 volts peak to peak, isn't it? Okay. Now, the first question is, what is the gain of this transformer?
2. We don't use it as a gain.
Right, so what is the gain?
1 to 2.
What has this signal gained?
Nothing.
Nothing, yes. Gain actually means you must get something, you know, something has got to be added to the signal. Nothing's been added. All we've done is change the ratio of voltage to current, really, haven't we? We haven't added any power. When we talk about gain, we've got to speak about power. So in a transformer,
It's both the same.
yes, the power output is equal to the power input, isn't it? So there is no gain in a transformer. And this is an important point I want you to try and get clear in your mind, the concept in your mind about what we mean by gain. To gain something means to collect something. Like if somebody give you 1,000 reals and somebody else took 1,000 reals from you, what have you gained? Nothing. Okay.
You say the multiplier.
Well, yes, okay, but basically what we're having to do, in the case of a transformer, there is nothing added in the way of power to the signal, is there? The signal coming out, power-wise, is the same as the signal going in. All we've done is change the voltage, but voltage isn't power. Right? It's like if I had here, say, 1,000 reals in 100 real notes, and then I got a mirror, so it looks as though I've got 2,000 reals, because you can see it twice. But there's nothing, it's all a trick. It's not real. You've not gained anything by that.
But again, means the power.
No, power-wise, it appears, power I'm talking about now, reality, as opposed to the way we represent power. Basically, all we've done here is change the way we've represented the power, isn't it? Do you know what I mean? Yeah. Because all I've said here is I've got 1 volt in, what's the voltage out? Okay, it's going to be 2 volts peak to peak. But we must understand that in a transformer is a passive device, isn't it? And that's really what we're talking about here. Because it's passive, no power is being added, so we know that the current at the output must be half the current at the input. Because VI is power input, isn't it? Must equal the VI output, apart from a little loss in the transformer itself. So, because of that, we can say that here, the gain of this transfer, there is no gain. The gain is 0. Right? It's not 1, it's 0. Gain is 0. I'm going to come back to this gain of 0 in a minute. All right? No gain. Nothing has been added in terms of power. The only way you can add power is if you use an active component. An active component takes a DC power and changes it or adds that power to the signal. Now here, in a power amplifier, I could say, for example, let's say I have 1 watt input and 10 watts at the output. Power. Now this is power now, not voltage, not current. We don't know what the current and voltage is, that could be anything. We can actually use a transformer at the output to change the ratio to anything we want.
Again, 10 divided by 1.
Yes. Now here we can talk about gain as equaling power out over power in, can't we? As a ratio of the two. Here we're using the ratio, so therefore we would say in this case the gain is about 10, isn't it? Because we've got 10 times more power coming out of the device. Where does that extra power come from? How can I get more power out than I put in?
From the power amplifier.
Yeah, from the DC power supply to the amplifier, yes. So we can't get something for nothing. That's where it's actually coming from. In other words, we must have here an active component of some description. Active meaning it's going to change that DC power into the signal power that we want. And that's when we talk about gain. So we cannot really talk about gain in a passive device. All we're doing here is changing the ratio of voltage to current. That's not an increase in power output. Increase in level. Okay, so we have an idea now about gain as ratio of power. And whenever we talk about gain, we should really be thinking of power ratios. Right. Okay. Now, once you understand that little point, and you've accepted that, now we're going to talk about logarithms. Okay, now we're going to talk particularly about logs to the base of 10. So let's talk about, first of all, indices. And let's take some examples. For instance, if I have 10 to the power 1, or 10 to the power 2, 10 to the power 3, etc., 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 what does this mean? For instance, what does 10 to the power 3 mean? No. Mathematically, what does it mean? Not the name given to it.
Multiply 3 times.
Yes, 10, that's exactly it. Multiply by itself 3 times.
Yes.
You know, not just the name. I know it means kilo if we put a name to it. But mathematically, it's 10 multiplied by itself 3 times, isn't it?
Yes.
Okay? So we could put that as 10 multiplied by 10 multiplied by 10. You know? And of course 10 to the power 2 is 10 just multiplied by 10, isn't it? 10 squared. What's 10 to the power 1?
10.
Yes, just 10 multiplied by nothing else, just 10. Okay, what about 10 to the power 0?
1.
Yes, you all remember that from your math days.
Yes.
In fact, anything to the power 0 is 1, isn't it? Whether it's 2 or 3 or 4, whatever it is 1 in that case. These are common logarithms to the base 10. You can take logarithms to any base you like, but in our case, when we talk about decibels, we're going to talk about common logarithms, logs to the base 10. Now, another way of presenting these indices is to do it the other way round. For example, if I said the logarithm, log, to the base 10. We normally write the 10 underneath here as a subscript. Log to the base 10 of, say, 1,000. The logarithm is the number you've got to raise 10 to get that number. So in this case it would be 3, wouldn't it? All right. It's a different way of writing it, but it's the way we've got to think about it. Logarithm to the base 100 is 2. Logarithm to the base 10 of 10 is 1. Agreed. And logarithm to the base 10 of 1, 0. Do you see how we've converted the two? Right. Okay. Now this, of course, is just revision work. You've done this before, so you know.
Just to write the power.
Basically, the logarithm of a number is the number you've got to raise 10 to the power of to get that number. We've got to raise 10 to the power 3 to get 1,000. We've got to raise 10 to the power 2 to get 100, 10 to the power 1 to get 10, and 10 to the power 0 to get 1. Okay? Quite straightforward so far. No problem. All right, now let's have a look at some other values. I'm going to just erase this now off this side of the board. Right, now it becomes a little more tricky. These are whole numbers, whole integers. All right, so the logarithm of 1,003, logarithm of 102, these are quite straightforward. Just count the number of zeros. How many times we're going to multiply 10 by itself. But what if I posed a question, what if I take the logarithm to the base 10 of a number less than 1? For example, 0.5. So now, yes. Now this is here we're dealing with positive numbers, okay, and these are whole numbers, aren't they? But what if I go to a number less than 1, such as 0.5? The logarithm of 0.5.
Multiply above a number divided by another 10 power of number divided by number.
Well, I'm not quite sure if I understand exactly your logic there, but all right, assuming we don't know the answer to this, what do you think it's going to be? Look what we're doing here. As the numbers go lower and lower and lower towards 1,
You get the negative result.
right, we've got to start talking now about negative numbers. Anything less than 1,
Negative.
we're talking about a negative number. Okay? That's essentially the bottom line. We're talking about a negative number. Actually, if you took, I don't necessarily expect you to know this offhand, but it is something worth remembering because we're going to deal with this. If you take the logarithm of a number less than 1, you really have to use either a lookup table or log tables to find this out. Or if you've got a calculator, does anybody have a calculator with logs on? You don't have a calculator with logs on. Okay. Okay. Then you'd have to look at the number. So if I have a log of any number less than 1, doesn't matter what the number is, a fraction in other words, then the answer here is going to be a negative number. Okay.
There is no any loss for negative numbers.
Well, actually, it's just a negative log. You take the log and then it's.
No, log negative 0.5 or log negative 1,000.
It actually. The log of negative 0.5 is like saying, what we're saying here, let me put x here as an answer. because this could be any number, that could be any number. Then we say 10 to the power x is equal to 0.5. If I put a minus sign in front of that, it's just like having a minus sign in front of this. It doesn't alter the actual number, the log. Okay? But in fact, because this is a number less than 1, because this number is less than 1, this would be a minus number. X itself would be a negative number. So it's like 10 to the minus x.
1 divided by 10 to the power x.
Yeah, 10 to the power x, or whatever it is equal to 0.5. And it's the same if we took fractions. For instance, let me choose an easier one.
No, I meant you can add this also in the way. It's equal to 1 divided by 10 to the power x.
Yes, it is. Yes, it is. That's right. Indeed. I'm going to come to that in a minute. In fact, we can even go even further than this. For instance, let's say I asked you this question. Log to the base 10 of, say, 0.1 is equal to 0.1.
Yes.
Now, that's a number less than 1, isn't it?
Yes, minus.
Yes. Now, the logarithm of 0.1 is a logarithm of a number less than 1. But we can also say it's the logarithm to the base 10 of 1 over 10, isn't it?
Yes.
So what do you think that answer is going to be? Well, what's the logarithm of 10? 1. So what do you think this one's going to be? Minus 1. Exactly. Minus 1. Remember, negative numbers for numbers less than 1. Just like milli, for instance, or micro. Milli is 1 over 1,000, isn't it? Or we could say 10 to the minus 3, neg 3. Do you see what I'm trying to say? Okay. So for numbers less than 1, we talk about negative logarithms, negative logarithm numbers, okay? We'll come back to this little one here because it's quite an important one we'll use. I'll tell you what it is in a minute. But you can work it out if you had a calculator that can convert to log. Okay, so I could continue this table here and say the logarithm of 0.1 would be minus 1. The logarithm of 0.01, minus 2, and so on and so forth, if you were to complete that in powers of 10. So that's fair enough. But when we come to numbers which are not exactly powers of 10, for instance 0.5, then it becomes a little more difficult. And we either have to look it up or we have to remember it somehow, because it's not a straightforward calculation, and it's outside the scope of this course to be able to do it by hand. But the logarithm actually of 0.5 is equal to minus 0.3. That's what he's equal to. Right. X is actually 0.3. I'd like you to make a little note of this because we're actually going to use this later in our work on decibels. 0.5 is minus 0.3. And again, we can talk equally about positive logarithms. For instance, if I asked you, what do you think the logarithm is? Now you know this. You have to accept this. Actually, it's 0.3 something something, but it's very close to 0.3. If you accept that, what is the logarithm of 2, do you think? What would be the logarithm of 2?
Point something, not positive, point something. Point something, positive.
Right.
Positive point something.
Yes, it is positive, true, because it's a number bigger than 1.
Yes.
So, a number bigger than 1. So it's going to be a positive number,
Yes.
true, and you should be able to tell me exactly what that number is going to be.
0.1.
No, 0.1.
0.01. 0.01.
One for, no.
You're all going round it, but you're not getting actually into it yet. Just think about it. It's quite clear.
1.4.
Right.
1.
Point.
It's based on this answer. If you look at it,
1, 2.
No.
It's based on
Point.
the size of
it's a positive number. We know that.
Point.
10 to the power.
See the calculator ثلاث مرات.
All right. First of all, if logarithm of 0.5 is equal to minus 0.3, 0.3, yeah, then this is exactly the same as saying logarithm of 1 over 2, of 1 over 0.5, I should say, isn't it?
Yes.
That is the same as that.
Yes.
Everybody agree with that? If you divide 1 by 0.5, you get 2. Okay? So we just neg that number. And if you neg that number, there's a positive number. So it would actually be plus 0.3.
Yes. Good trick.
Oh, it's not a trick. It's not a trick, but
I know.
it's an important number. We can actually take any number here and look it up, and it would be the same if you went positive or negative. But the reason why I've chosen 0.5 and 2 is because we're going to use this a lot in our work. So let me just repeat again what we've talked about here. I normally have a calculator with me with logs on. Nobody has one, eh? No log calcs.
No.
You can do if you wish. I don't mind. Yeah, I might bring mine in on Saturday actually.
My plane is not with me. Yesterday I was in the jail, so
Were you?
yeah.
Why? What happened?
Don't ever drive in a Medina street driving more than 80.
Logarithms. We can express numbers less than 1. If we have numbers less than 1, they are negative numbers. Okay? For example, 0.5 would be minus 0.3. And numbers in between, for instance, between 1 and 10, how do we express those? Well, for example, the reciprocal of 0.5, 1 over 0.5, must be the negative of this, mustn't it? If you take the reciprocal 1 over, you negative of this. So the negative of this, 0.3. So that's how we can use logarithms. And we can also, if you think about it, join this information in one go. For example, let me just put down an example here. Let's say we have this. What would be the logarithm for those two? Of say 200.
We can split
Right.
100 to 2 and times 100.
That's exactly right.
We go
Yes.
to this side.
Okay, we can rewrite this in a different way, couldn't we? We can say it's the logarithm. This is the same as saying it's the logarithm of 2 multiplied by 100, isn't it?
Yeah.
Okay. Which, if you multiply two numbers together, you can add their logarithms. For example, if I multiply 100 multiplied by 10, that gives me 1,000, doesn't it?
Yes.
It's 2.
So in other words, it's 2 plus 1 is 3. Right? So you add the indices in order to get the multiplication. So it's the same here.
2.2.
That's right. It's actually equal to the logarithm of 2 plus
Logarithm
the logarithm of 100, isn't it?
distribute the logarithm.
That's right. Which we know the logarithm of 2, we learnt that was 0.3. And the logarithm of 100 is 2. So the answer would be 2.3. 2.3. Do you see how we did that? And indeed, this is how you do any logarithm. You can split it into the...
Use the calculators.
You can use the calculator just the same, yes. In fact, you would need to use a calculator or a lookup table of some sort to get numbers between 1 and 10. Right. And numbers less than 1, of course, are just the reciprocal of these. So if you remember that the logarithm, this is the important one, the logarithm of 2 is equal to 0.3, then the logarithm of 0.5 is neg 0.3, isn't it?
Yes.
Minus 0.3, because it's 1 over 2.
Yes.
That's right. So this is really a little bit of revision now, which you probably learnt before, and we're just reminding you about logarithms and how we use logarithms. Okay. Now, let's see how this fits into what we call decibels. Word gain again, this is really what we're talking about here. As a ratio of 2 powers, okay? Power 1 over power 2. Or, if it was an amplifier, it would be power output over power input. Do you agree with that?
Yes.
Now, what we do is this. In electronic work, when we talk about gain, we usually take the logarithm of this ratio. Okay? We use the logarithm. We don't use the linear ratio, we use the logarithm of the ratio. It'll become a little bit clearer later why we do this. So, we can also say that the gain is equal to the logarithm to the base 10 of this ratio. But of course it's now a logarithm. In order to define a logarithm, we express this in bells. Okay? And because this number normally is a fraction or something like that, we multiply it by 10 and call it decibels, tenths of a bell. So the normal way we use it, you probably wouldn't use bells, you would use decibels, which means it's the logarithm of the base 10 to the base 10 of this, multiplied by 10, and then the answer's in decibels, okay, or dBs. Decibels, tenths of a bell. Basically, these are the same, except by multiplying by 10, we get it in dBs.
Standard multiplier.
Remember, we're only taking the log of this, and then we multiply the result of that by 10. And that gives me then the answer in decibels. Okay? Let me just put in a simple example up here to see that we've understood it so far. It's always good to start with an amplifier as an example. We have, let's say, 10 milliwatts as our input, and let's say 1 watt as the output. This is in power, this is a power, of course. And the question is very simple. What is the gain in decibels? If somebody says, okay, there's an amplifier, that's our input, that's our output, what is the gain of the amplifier, not just as a ratio, but in decibels? So we've got to apply everything we've got. If you get the answer, just keep it to yourself for a moment and let everybody work it out, and then we'll go through and work it and see what the answer is. On what output power? So very simply then, the gain is going to equal the logarithm of the output. Now you can put the output if you want in milliwatts to bring it to the same units. You can say 1,000 over 10, can't you? Right, that's right. And don't forget to multiply your answer, what you get there, by 10 to bring it to decibels. So the logarithm of 1,000 over 10 is 100. Logarithm of 100 is 2. So it's 2 times 10. Right, equals 20 decibels. There's no negative number there, it's all plus. You can put the plus in front if you wish to make it clear that it is plus. It's a gain, a positive gain. We're adding power. We've got more power output than we have at the input. Now, if this power was less than the input power, this could be, for example, an attenuator to reduce the level of the signal. Then, of course, we would end up with a negative number here because the ratio here would be less than 1, wouldn't it?
What the output and input and then
Yeah, for instance, if I put 1 watt in here and 10 milliwatts out,
be negative.
yeah, all we do is reverse this, and we end up with minus 20 dB as a gain. So, that tells us something for a start. An example, let's say I have a circuit which is actually an attenuator.
Anyway.
Now, by attenuator, to attenuate means to cut or to reduce
Yeah.
the level of something. Attenuator is like the opposite of an amplifier. Here, where your output is actually less than the input. Let me choose a different example, or a different set of numbers to give us some practice. Let's say the input here is 100 milliwatts, and the output is 1 microwatt. Okay, and what is the gain? Now notice, I'm using the same word gain. I'm still using the word gain. Very important to remember this. You can still talk about the gain of an attenuator. The only difference being it'll be a negative, or if you've done it correctly, a negative number. Let me do this calculation then, so that you'll know what we're doing here. The gain we're going to use the same formula. There's no difference in formula. All right. Let me just write the formula down first. Then it's out over in, always, multiplied by 10, and that's our answer in dB. Okay, let's just put the figures in here. What's the output power? 1 microwatt. Let's bring everything to microwatts to make it easier. We must bring them to the same units. So that's 1 divided by how many microwatts are in 100 milliwatts?
100
How many microwatts and 100 milliwatts?
Yes.
100 minus.
No, wait a minute. How many microwatts are there in 1 milliwatt?
100,000.
100,000.
Yeah. The answer to the second question I asked, the number of microwatts in a milliwatt is 1,000. Now these sort of calculations you should practice and practice and practice on, because this is the sort of thing you should be able to do quickly in your head. But even if you used a calculator, you've got to bring these to the same units somehow. You can bring them to watts, microwatts, milliwatts, whatever. You're going to get the same answer, as long as the units are the same. In my example, I said I'm going to bring everything to microwatts. So we've got 1 microwatt divided by how many microwatts here?
100,000.
100,000, yes. 100,000. Because there's 1,000 microwatts in 1 milliwatt. Anybody not sure about that? What I'm saying is 1,000 microwatts is equal to 1 milliwatt. Because, you see that? So 100 milliwatts is 100,000, isn't it? I'll put it in figures here. So 1 microwatt divided by 100,000 microwatts. That's what we've got to take the log of, and then multiply it by 10. Okay, let's do that. What is 1 over 100,000? What's the logarithm of 1 over 100,000?
5. Oh, minus 5.
Minus 5, yeah, exactly. Exactly. Minus 5
50, a bit of the-
times 10. All right.
Can you find another way easier?
Well, that gives me 50 dBs. minus 50 dB, I should say. Don't forget the minus. So none of these were right.
Excuse me. Can you add another easier way or something?
1 microwatt.
Yes, in a minute. Yes.
1 micro is equal to 1 times 10 to the power minus 6.
Indeed it is. You could do that way if you wish.
And 100 milliwatts
Yes.
is equal to 100 or 1 times.
Right, well, let me just write it. If you want to bring it to watts in that way, let me just put it over here, because we've all got to be able to do this. You said that 1 microwatt, right, is equal to 10 to the minus 6 watts.
It as a minute.
Right, now, you see what you're doing there, you're using the calculator, okay? No problem with that, but when it comes to whole numbers, exact multiples of 10, I find it better to work in indices. If you're going to use a calculator, you're going to end up with 0.00000 something. Okay, no problem with that. It's still the right answer, but you've got to count your decimal point.
Yes, there will be one.
It'll be 5 zeros, will it? Or 4 zeros, and then a 1. That's right, well, that's 10 to the minus 5. You see? As long as you can do that, there's no problem. It's going to give you the same answer. What I did here, I changed everything to microwatts. But if you don't want to do that, or if you find that a little confusing, stick to watts. You know that 1 microwatt is 10 to the minus 6 watts. You know that 1 milliwatt is 10 to the minus 3 watts. Well, we've got 100 milliwatts. So it's just a matter of resolving this equation. And we can cancel here to here and make that 10 to the minus 3 over 100. Okay? Or you can do it the other way and say that this, let me just put it in a different colour, is the same thing as saying, well, it doesn't really matter. You can say 10 to the minus 3 over 100, or 1 over 100 times 10 to the power 3. It's the same thing. You're going straight from here to here. It ends up to be the same. So it's 1 over 10 to the power 5. Now 1 over 10 to the power 5, 10 to the minus 5, isn't it?
Yes.
And it's the minus 5. It's that indice we want. That's the answer to our logarithm. Minus 5. So that would be minus 5 bells, multiply it by 10 to bring it to decibels, minus 50. Don't forget the minus. It's very important. Be careful in multiple choice answers here. You know, they'll probably give you a plus and a minus answer. And if you've been busy calculating, you say, yeah, it's 50. And then you don't think, and you see 50, right, that's the answer. Not looking at all your answers, there's a minus 50. That's the right answer. So be very careful with that. Just think a little bit about it before you... And so I'll give you a couple of other examples if you wish, because it is an important thing which... Basically, the dBm is a power with relation to 1 milliwatt. Okay, let me just write this. To 1 milliwatt. We can use the dBm to measure absolute power. Without knowing input and output, we can use it to measure absolute power. And I'm going to give you, first of all, an example of this. A little example of how we would use dBm. Now here, we don't need, we haven't got an input and an output. We only have an output. I haven't told you what the gain of the amplifier is or what its input is. And what I want to know is, what is the power in dBms? I've given you the power in watts. What is the power in dBms? Now, before I go through this example, does anybody want to think about that and perhaps hazard a guess of what the answer is for this? Or do you want me to put the full...
2 million. 1 million dBm.
Now, this dBm is a measure of power. What's dBs a measure of? It's a ratio, yes, that's right. Now, there's a difference here. Big difference between dB and dBm. dB is a ratio of powers.
Yes.
It doesn't have any units, right? Apart from dBs. There's no, you don't talk about watts or milliwatts or anything like that. It's a ratio of two powers. Okay?
And dBm you just reserve there, it's the ratio of power.
But it's fixed to 1 milliwatt.
There is a difference.
So therefore, it's a reference, that's right. So now you can say it is a measure of absolute power because we're relating it to a fixed value. So we know. For instance, if I said to you, I've got an amplifier of, and it has a gain of 100 dBs. What's its output power? You can't tell me. You don't know that because you don't know what the input is. But if I said the input was 1 milliwatt, then you know precisely what the output power will be, the power of the output. Not just the gain as a ratio, but an actual power. So the dBm is a measurement of power, not just a power ratio, because we're always referring to 1 milliwatt. In other words, how much bigger is this power compared to 1 milliwatt?
2000 milliwatt.
Yes, this is 2000 milliwatts, isn't it? Compared to 1 milliwatt. We use the same formula, except we must remember that the power in dBm, because dBm is a measurement of power, is equal to the logarithm, again we're going to use log, to the base 10 of the power divided by dBm. Sorry, divided by 1 milliwatt.
1 milliwatt, yes.
That's right, divided by 1 milliwatt. And then we still multiply it by 10, but the answer now is in dBm. Okay, that's the formula we're using, and if we put the figures in for that, for this example, we can say therefore
This M means milliwatt.
yes, the little m at the end reminds you that we're dealing with the ratio of power to 1 milliwatt, dBm. Okay,
32 dBm.
that reminds you, the little m tells you with reference to 1 milliwatt.
32
Mm.
dBm.
Yes, probably will be.
32.
Let's work it out. Basic, I'm going to split it out a bit here. That's equal to the logarithm to the base 10 of 1,000.
1,000.
Yes.
Multiply with logarithm of 2.
Yes, plus the logarithm of 2, isn't it?
Yes, which is my 0.3.
3.3 times 10 to
And all that is multiplied by
3.3,
10,
yes.
of course.
33.
Yes, that's right. So it would be the logarithm of 1,000, which is 3.
Yes.
And we already know, because I wanted you to remember this, that the logarithm of 2 was 0.3. And all that, of course, is multiplied by 10. So that gives me
33.
33
33 dBm.
dBm. 33 dBm. So we have we're talking about two different things here, the dB and the dBm.
What do you use the DPM for? What's our gain now?
You can use dBm if somebody says, for example, let's say you connect a modem to a telephone line. Now, the PTT will say, according to their network, they will say, whatever you do, don't put more than 30 dBm. Actually, that's a big figure, but let's say, choose that as an example. Don't put more than 30 dBm power out onto the telephone line. Okay? That's maximum power. It is a measurement of power. And what it means is 30, in that case, 30 dBm, right, is the amount of power compared to 1 milliwatt. And we'll do some more examples, but what we're saying is it's usually a measurement of small power, not usually big power, small signal power.
What will happen if we fix this model more than 30 degrees?
Well, in that example, probably what would happen is we did start to interfere with other lines. There's a certain maximum power you can send down a telephone line because of the way the cables are together. If you put a bigger signal down, you start to interfere with other lines. Yes, what they call crosstalk.
Yeah, exactly.
That's right. So you've got to be careful with your modem.
But you always fix it from the BTT, not from the modem.
No, I'm assuming everything's all right on the PTT. There will be, it's not just in this country, anywhere. Anywhere where you have a telephone system, there must be a certain maximum power level that you're going to launch, what they call the launching power level, and from your modem. I think actually in this, it might be 0 dBm or 10 dBm, I'm not quite sure.
Why they are talking about the certain level inside 1 milliwatt? Why this difference?
Why 1 milliwatt?
Why this difference?
I don't know. I'm not quite sure why 1 milliwatt. It doesn't really matter what it is as long as it's fixed and everybody knows what it is.
So what is important for it? You said, can you repeat?
It's a measurement of power, usually small amounts of power, but it's a measurement of power.
Why don't we immediately say, don't send us modem to this?
Probably because this is logarithmic.
It's converting the 2 watts to a different way of measurement.
Yes, it is.
Because
Yes,
you can also go that way.
that's right, you can do it either way, yes.
Yeah, like saying 2 watts or 200
Well, first of all,
milliwatts.
yeah, this actually brings out the whole point of why do we use dBs? In other words, why don't we just say the gain of an amplifier is 100 or 1,000?
Yeah.
Instead of using decibels. And the answer to this really is to do with the way we're using the power. Initially, you probably are aware that decibels were first used, the measurement of dBs was first used to measure sound, how loud a sound was. And they measured it in decibels because the ear itself responds to sound logarithmically. In other words, you can double the power of a sound. Say you had an amplifier and a speaker. You multiply the sound power by 2, it doesn't double the impact on the ear. In fact, you might not even notice much difference. Okay. Now, if you double the sound power, you're increasing it by how many dBs? Multiply by 2. If you double or multiply by 2 the sound power, or any power, you know, how many decibel change is that taking place?
Not change.
Like only the power?
Power by 2.
Power by
The
2.
input and the output?
Yes. If you multiply by 2,
Not change.
We're not changing anything, the same.
you're multiplying the power by 2.
Only the
No,
output power.
that again will change
The gain will change, yes.
because the output will be maximum more than after if you more
Again, it is
amplifier.
increased.
So what is the gain if you multiply by 2?
Never.
Yes. What is it in decibels? Here's a question. Have we copied this down?
Yeah, you add only one figure. You add one.
Right. Now what I'm saying, the question I'm asking is, and this is just an example, but it's a good example. If you double the power at the output of an amplifier, let's say an audio amplifier with a speaker, and you double the power, let's say it was 100 watts, you double it to 200 watts.
0.3.
You add 0.3.
0.3 times 10,
Yes.
3 decibels.
Yes.
Exactly. It's a 3 dB change. That's all, 3 dB.
Again, please.
If you double the power, it means you multiply by 2, doesn't it?
Yes.
So the ratio is 2 to 1 between the old power and the new power.
Yes.
So the dBs is the logarithm to the base 10, right, of 2, right, and then multiply that result by 10. Now, what did we say the logarithm of 2 was? Between it, because it, yeah, 0.3.
Yeah.
It's a number between 1 and 10. So that becomes 0.3 multiplied by 10, 3 plus 3 dBs.
Yeah.
So if you go into a shop which sells stereo amplifiers,
Yeah.
and they say, right, we've got this amplifier here for, I don't know, 500 reals, and it has an output power of 50 watts. 50 watts. And then he has another amplifier which has an output power of 100 watts. Right? Notice only a 3 dB change, that's all. Just 3 dBs difference between the two. But he's not going to tell you that. He's going to say, this, in big writing, is a 100-watt amplifier, whereas this little thing is only 50 watts. Right? And there'll be a big difference in price too. But you're only getting 3 dBs difference in...
Because they double.
Yes.
So the 3
This is
dB.
multiplied by 2. In that example.
So
I'm lucky.
In other words, 3 dBs to the ear, not much difference.
Because
how
in
much
this-
would be the difference?
Well, probably you would say a 10 dB change in sound would be significant. You would hear significant. Now, if you talk about 10 dBs, right, that's 10 to the power 1. In other words, your difference between your amplifier at 50 watts, if you really wanted a 10 dB increase, you need 500 watts to make appreciable difference. Now, a lot of people in the shops, you know, I've been into these shops and I said I wanted this particular amplifier, which is say 50 watts. And he'll say, no, that's the old model, that's last week's model. Look at this one now. For an extra 1,000 reals, you get 100 watts. So what? You know? But to him, a big deal, you know?
In the computer shop, you find a speaker it is 60 watt, and the other speaker with a little more money, with 100 or 120.
Yeah.
I select 120.
Did you notice those 3 dBs? Well, if there's not much difference in price, fair enough.
You know,
Yeah.
now I recognize I'm so clever.
Before.
Well, you can at least baffle the shopkeeper and say, well, that's only 3 dBs, and he probably wouldn't even know what you're talking about.
What is the
But-
what
But
is
you
the
find it
master
now
filter
illegal.
for you, DB?
Well, the example I gave was sound, okay? But I mean, even in radio broadcasts, remember what happens when you transmit a radio signal? Say from an omnidirectional aerial, omnidirectional antenna. Radiates in all directions. Now, let me ask you a simple question. No mathematics involved here. You've got an antenna here, and let's say 1 kilometer away you have a receiver. Right? Now let's say I have another receiver 2 kilometers away instead of 1 kilometer. And I'm going to measure the power level that I'm receiving. It's only going to be very small. We're talking about a few microwatts perhaps from the transmitter. Do you think the power level at 2 kilometers is going to be half as it was in 1 kilometer?
The power?
The power level that you're receiving from that transmitter.
Because you double now the distance.
Double the distance, yeah.
The more this.
It's not linear, exactly. It is not linear. It's a bit like the way your ear works. It's not linear. In fact, it decreases quite considerably as you go further away. Because it's like blowing the balloon. The energy is going in all directions. So, you know,
Decreasing more, you mean?
decreasing a lot more than half, yeah.
Maybe a quarter.
Oh, a lot more than that. And the easiest way to measure it, right, is in as a logarithm, because of the scale.
Is also not linear.
No, as long as we're not trying to make it linear, we're trying to get it closer to reality. That's all. It's not exactly proportional, but it is logarithmic. The way it decreases, it is logarithmic, but it isn't exactly equal. But it'll give you a much closer, much better representation of your power level if you measure it logarithmically. So it's not just sound, it's also strength of radio waves. We can also speak about the strength of radio waves changing logarithmically. And that's the reason why we use logs.
What about the same distance in the first example? If you double the power,
Yes.
is it affected?
Yes, it will do, but only by 3 dBs.
You're saying here.
If you double the power
Yeah.
from the source,
Yes.
you will find it's more just 3 dB.
3 dBs, yes.
You're saying here we have two antennas.
Right.
One from the distance between the 1 kilometer, and the distance between the first antenna and the transmitter is 1 kilometer.
Yes.
Then the other antenna will
There's another kilometer, yes.
Yes, decrease the power to a half.
No, it'll decrease it much more than a half.
Then more than half.
Much more than a half, yeah.
Because the power of the signal is getting weak.
Because it's getting weaker and weaker, it's expanding. So it can be shown it's like a logarithmic relationship between them. It's like a logarithmic relationship.
This is the way a logarithm sign is drawn, isn't it?
Sorry, that's the, what is that?
A logarithm.
A logarithmic curve?
Yeah.
You can draw it, yes, okay then. To the base 10, are you saying?
Yeah.
Okay, yes.
It doesn't matter to what base, I just on what.
Okay. Notice though that the change gets, the rate of change gets faster and faster as you get away.
It gets,
yes.
because you
That's
see
right.
1,000, it goes to.
That's right, yeah.
That's why it's going
Yes,
up straight and down straight.
yes.
But over here, it's there's a slight small because of the points.
That's right. As you get, if you're very close to the antenna, then of course the change, because you're so close, right? What you're talking about there, for instance, could be distance compared to signal strength. When you're very close to the antenna, then if you double the power, right, you probably would notice a big difference. It's like having a transformer coupling. But as you go further and further away from the antenna, the effect of changing the power has less and less effect on your signal. But the dBs, right, the decibel, if you measure it as a logarithm, will always be the same. Double the power, it'll be a 3 dB change.
So that we have a channel for the email here, mail channel. Sometimes we request for us to increase the power from 40 to 80.
What's this for? Sorry. For
Because in our channel here, for
What
mail
channel?
services.
what channel? Are you talking? Oh, you're talking about. Are you talking about trunking radio or something?
Yeah, repeater.
Oh, repeater for what?
For mail services.
Trunking radio.
No, that's, it is
Just separate.
control one. The control. It is the repeater one. Sometimes we found it 40. We said no, make it 60. So that you said it is just the gain will get only plus 3. Is it effective?
It depends. Plus 40 watts.
What?
Watts. It is watts you're talking about.
Yes.
Okay. Then if you change it from 40 watts to 80 watts, then it's a 3 dB change. Yes.
It's not that much. So, and we get a problem sometime, for heat.
Yeah, that's true. Yeah. It's the same with these. Let me give you a very good example here. The HF transmitters at the airport. Those are the ones that use 10 kilowatts. 10 kilowatt transmitters, right? Now, 10 kilowatt transmitters are very high power. Agreed?
Yes.
Now, what do you think they'll do if they reduced it from 10 kilowatts to 5 kilowatts? So 3 dB change. Do you? All right. Remember the HF. The HF works by the ionosphere. The wave is bounced back to the ground, isn't it?
Yes.
Right. So let's say we've got communication, say between Jeddah and London, or wherever it is, some distance away. So we're using a certain frequency to get communication. And the guy in London can hear us and transmit to us, no problem. And we're transmitting on 10 kilowatts, 10,000 watts. What difference do you think it makes if he reduces his power to 50 kilowatts? The only difference is a 3 dB change here in his received signal.
From 10 to 50?
Sorry, from 10 to 5 kilowatts. All we get is a 3 dB change. Half power, isn't it?
But he received.
Yeah. I'll tell you something else. I communicated from, on a ship this was, from South Africa to London, right? By HF. Now, on the ship is made of metal. This was in a radio cabin made of metal. I had a transmitter in the radio cabin, and from the transmitter, the antenna came out on a, it wasn't a waveguide because it was lower frequency than that, but it came out on a conductor, and I had like a switch to switch it onto the antenna, which was strung across 2 masts on the ship. The idea being that my transmitter connected to that cable radiated the energy. Right? And I'm radiating on HF to London. Right? Now my transmitter was only a 100-watt transmitter.
100.
So I got hold of the guy in London, sent him the messages, he sent me the messages, no problem. And then I looked at my switch, and it wasn't even connected.
Not connected?
Not even connected. I wasn't even connected to an antenna.
How it is?
Exactly, how? It's just leakage out of the cabin window. It was equivalent to transmitting at about 1 watt. 1 watt, equivalent.
But it's
And he received
100.
it.
Should be 100.
Should have been 100. Here we're using 10,000.
What?
Why? Because the people who make the big transmitters want to sell us them, that's why. Not necessary. Completely unnecessary.
Strange.
It's not the transmission we must be aware of, the receiving sensitivity.
Well, there's a lot involved. Remember, it's a little bit like when you're talking about range. And I said it's line of sight. I'm not talking about HF now for higher frequencies. But if somebody goes in front of us, then you might lose it. So it's a little bit like that with radio communication. You cannot say, I'll pump more and more and more power, and that will give me better or longer range or better signal. Doesn't necessarily mean that. There are so many other factors involved. As you say, sensitivity of the receiver, the position of the receiver, any interference, for instance, or noise can affect it a lot. It's not just power of the transmitter that makes all the difference. Take our microwave links, microwave point-to-point I'm talking about. How many watts are they? Milliwatts. Transmitted milliwatts.
Not right.
The transmitter actually output is in it's measured in milliwatts, not even in watts. It's measured in milliwatts.
What about those people who, the designer I'm talking about, who designed these things by thinking, why? Is mathematician.
Why did they design the transmitter for 10 kilowatts?
Yeah, because we can't make a coverage.
The only time that will make a difference is if you've got somebody else transmitting in the world on exactly the same frequency
Interference?
and they interfere. So the 10 kilowatts will be that few dBs higher and therefore probably likely to beat the guy with only...
For safety.
To show the muscles?
That's what it is.
Thinking.
10 kilowatts will win out then, but all other things being equal, that's probably the reason why.
Only in business.
Yeah, but for most times that might not happen, you see. Most times you don't need 10 kilowatts. You could do it with much lower power and still get the communication. Anyway, whether we like it or not, we've still got to measure our power ratios in decibels and our, for small signal powers, in dBm. This is true for when we're talking about radio as well as telephone and modem circuits, they use the DBM. Okay. So the way we use the calculation is the same, except with DBM, it's always relative to 1 milliwatt. That's fixed. So therefore we can say DBM is a measure of absolute power.
Small.
Usually small power, yes. You wouldn't normally, if you're talking about a 10 kilowatt transmitter, you wouldn't express that in DBM, it would be just too big. But for small powers, like the power output of a modem going onto a telephone line, like the power output of a receiver, or the power input to a receiver, because we're dealing with very small power levels there. Okay. There is actually a printout, a handout I've got here on the DB and the DBM. Okay. Let me just put down another question, or another couple of questions. Actually, before I do that, there's one other thing which I think is an example here, with an input and an output.
It's an example.
This is another example, but now I'm going to make it slightly different. And I want you to think about this first, before I give you the answer. I'm first of all going to give you a little bit of information. The input impedance of this amplifier is equal to the output impedance. We're going to assume that. This is Z. We're going to assume that for the purpose of this question. All right? Now I'm going to give you this. I'm going to say that the input voltage, and as far as we're concerned, that means RMS, although it, as we'll see later, it doesn't have to be, is equal to, say, 1 millivolt. And here, the output voltage is equal to 100 milliwatts. Millivolts, sorry, it's a voltage. Okay. Now, here, the difference between this question and the previous examples we've taken is that we're talking about an input and an output voltage. This is the difference, not an input and an output power.
Power, yes.
Okay? But I've given you a bit of information here, which if you think about it, you should be able to figure out what the input and output power ratio, remember it's talking about ratio here, the ratio between the input and output power. What I want to know is, not dB, I want to know what the gain is in decibels. No, it's not zero. It's not zero. The gain in dBs.
Will be 1 million, will be 100 milliwatt.
Again, DB.
Yes.
0 times 10.
Will be 10 to
You have to think about this a little bit. It's
40, I think.
there is a gain.
40.
There is actually a power
40
gain.
dB.
You, for amplifiers, you said that.
In dB or dB?
dB for
dB. The gain in dB.
40.
40.
Oh.
Oh, you're looking at the thing.
Because I can't explain how it's come like this.
Okay. Well, okay, let me just put down some of these answers you're getting. 40 dBs is one answer we've got.
The formula you gave us before says that if the input impedance is equal to the output impedance, the gain is going to be 1. Because the gain is equal to the output impedance divided by...
No, I didn't give you that. I'm sure I didn't say that. Maybe I gave you an example where the input and output voltage was 1.
He said again, yeah, I remember what he replied. He said again it will be the output will be defined by input impedance, so that we make substituting, so all to find the gain alpha and beta.
Are you talking about an operational amplifier?
Yes.
That was voltage gain. That wasn't power gain.
But he's talking about lower
Power gain here. Yes. This one is actually probably easier than that. But if you just think about the input power and output power equaling, make up a value if you want, 1 kilo or whatever it is you want. It doesn't matter because it cancels. But what I want you to think about, first of all, is if I said I've got an input voltage here of 1 millivolt, for example, what's going to be the input power by means of a formula? How would you find the input power to that?
E
What?
is equal to I times V.
Yes.
We've got
If we don't know I, but we do know V and we know
Type B.
R,
B
power
power
equal
2 divided by R.
E square over R.
V squared over R.
yes.
That's right. So again, we're going to use the same formula of power ratios because that's what decibels are, power ratios. Not voltage ratios, power ratios. But to find the input power for this amplifier, we can say it's equal to V squared divided by the impedance. V squared over R if the impedance, we assume it's a resistance. Okay.
So
Right, V squared over the impedance. And the output power right, is also equal to V squared over the impedance. But in this case, this is the output impedance, and this is the input impedance, and the input and output voltage.
so it's V out squared or divided by V input squared.
Right, because the impedances cancel, don't they?
Yeah.
That's why you didn't really need to know the impedance to answer the in question. So, rewriting this, we can say, therefore, the gain, and we're going to use exactly the same formula that we used before, logarithm to the base 10. But now let's have a look at our ratio of powers. This is our input power, that's our output power, and it's output divided by input, isn't it?
Yeah.
So it's V output squared over Z divided by V input squared over Z. Well, the Z's cancel, don't they?
Yeah.
We can ignore now the actual value of impedance. And then, of course, we have to multiply that by 10, and that gives me the answer in dBs. Does everybody follow what I did here?
Yes, yes.
Right?
Output divided.
That's right. Remember, by the definition of decibels, it's a ratio of power, not a ratio of voltage. So we really need to take power into account, input power and output power. And all you need to do is remember your formula. We don't have the current, so we use the voltage. We have the voltage, we have the impedance, V squared over R, or Z, same thing. And they're equal. Z output is equal to Z input, so they will cancel. So that gives me the logarithm to the base 10 of V out over V in squared times 10 dB. Does everybody agree with that?
Yes.
Yes.
That is the same as this.
Yes.
Right. Now, if you take the logarithm to the base 10, if you take the logarithm of a number that's squared,
You
Double.
multiply.
you multiply by 2, don't you?
Double this.
Yeah. The logarithm is multiplied by 2.
Yes.
Yeah.
Okay, so what I'm saying is that's exactly the same as saying V out over V in times 20 dB. Because what I've done here, I've removed the square and I've multiplied by 2. Still got the 10, of course, so it's now 20. Right. And the V output is 100, the V input is 1.
100 logarithm.
So the logarithm of that is 2 times 20 is 40. That's correct. What you said was correct for 40 decibels. Just rewrite this right here. That completes it. Are you hot? You think? You're hot. You're not sure if you're hot. For the purpose of this calculation, we would not go any more deeper than that.
Because when you don't give us the impedance, we assume that's the same.
You've got to assume the
But
is
when
the
you give
same.
us the impedance, you must calculate the power and the...
Then you would have to calculate power, but that is an unusual type of question. I've not seen that in the exam.
What's that?
What we're saying here is that really what we've done here is just calculated the input and output power, isn't it? Instead of being given the power in watts or milliwatts, we calculated it. And the way we calculated it was using V squared over the impedance. So strictly speaking, we need to know the impedance. But if we knew that the input and output impedances were equal, we don't need to know what that value is, do we? They cancel out. And what I'm saying is, in a practical question, it will assume, if you get a question on this, where they only give you the voltage, imagine you've got a test question in the exam. They give you an input and output voltage, and they don't mention anything about impedance.
And he request dB.
Yeah, and they request the dBs. Then you've just got to make the assumption that that impedance and that impedance are the same, and then we can use this formula. Now, if they don't, of course, if they give you an impedance, then you have to calculate that power, calculate that power, and then do the way we did it before. But
You give us the power.
yes,
And,
I could give you a voltage or I can give you a power. If I give you a voltage and don't mention impedance, you just assume the impedance are the same, and this is what you use. So if you've got a ratio of voltages, you multiply it by 20 to bring it to decibels. If you have a ratio of powers,
yeah,
you multiply it by 10.
by 10. Yeah.
That's the difference. The difference between 20 and 10.
The power and the voltage.
That's right. This is a voltage ratio.
Voltage, you multiply with 20.
You multiply by 20, and that's a very important difference.
Yes,
If you only get voltage ratio, multiply by 20.
20.
If you get a power ratio,
multiply by 10.
multiply by 10.
What about current?
I've never seen a question involving current, but you can argue it's the same. If I gave you two current ratios, it's still 20, because remember power is proportional to the square of the current.
What about the
I squared R.
output current or the input or output?
Well, output over input is what you would normally use, yeah. Output over input. But I've never seen questions involving current. Let's not bother with that. But it would actually be the same answer. Okay, so we've done the decibel, the dBm, and we've been able to find the gain using a voltage ratio if we didn't know the power ratio. We should know that if we attenuate a signal, then that means we have a negative value of gain, doesn't it? A negative dB. Right. Whereas if we amplify, we add energy to it, power, we increase. We get a plus dB value. And I'm going to put a little example here of a complex system. In dBm, calculate the output power of this system in dBm and the output power of this system in dBm. Oh no, let me make it a bit more interesting than that. This one the output in dBm, this one the output in watts. Yes, 100 dB gain, and the attenuator, that's an attenuator. So now it's a minus dB, you see. So we're amplifying it, then we're attenuating it, then we end up with a result. And same here, we amplify it, attenuate it, we get a result. The only difference between the two questions is here I want the output power in dBm, here the output power in watts, or milliwatts, or whatever it is. Now, this is, to answer these questions, we're using our knowledge the other way around. Here I'm giving you gain in dBs. Well, here I just want the answer in dBm.
First one will be-
Input is going to be.
Oh, I see. You're calculating the input, are you?
Yes. 10 watts. No, not 2 watts.
There's an easy way and a hard way of doing this. It looks as though you're all doing it the hard way. When I show you the easy way, I mean, you know. Oh.
Because 40 dB will be the logarithm of 10,000.
Right. Well, do we need any logarithms here?
3,000.
No, we have everything deep.
We have everything in. Yeah, the output I want in dBm. The input is in dBm. There's no need to change it. Stay with dBm. And now we're going to see one of the advantages of using a logarithmic.
100 plus minus
40 dB.
40 dB. No.
Well, we begin with 40.
No,
This is 40 dBm.
Yes.
40.
Is the output going to be 40 dBm?
40,000. No, 40 dB the same will be 40 dBm.
I'm asking you. Is the output going to be the same as the input?
No.
Difference between
It's
amplifier and
increased, yeah.
Yes, 40,000 and 40,000.
It is increased. Because look at what we've got to go through. We have an amplifier with a gain of 100 dBs, followed by an attenuator with a gain of 60 dBs. Now what you can do, you can look at these two guys as one unit with one particular gain. What's the gain going to be?
40 dB.
40 dB.
Yes.
And
That's
divided by
right.
1 million.
40 dB. This now brings out one of the advantages of using logarithms like this. When we're, instead of multiplying and dividing, every time we go through an amplifier or an attenuator, we can just add and subtract the dBs. So here we've got 100 dB gain. Here we have minus 60 dBs. 100 dBs, right, is 10 to the power 10, isn't it? Am I right or am I wrong?
Yes.
10 to the power 10 is 100. Yeah. And minus 60 dBs is 10 to the minus 6. Okay? Now, to get the total, mathematically, okay, you can take the difference in the indices. In other words, 10 to the power 4, or 40 dBs is the gain. 100 minus 60, 40. So that's the first thing we can do. We can say that this is like 1 unit with a gain of 40. Just by using addition and subtraction. You know, we don't have to bring it to a ratio. It's not necessary. We can just use addition and subtraction. Okay, here we have a gain of 40 dBs. Now, it so happens I've given you the input power in dBm. That's a big advantage. You don't have to change that to watts, because I don't want the output power in watts, I want the output power in dBm. So if the input power is dBm, and we have a 40 dB gain, what's the output power?
Divided by 1 million.
40 dBm
Yes.
plus 40 dB, 80 dBm is our output.
Direct?
Direct. 80 dBm.
So that is the
ridiculous.
measurement is dB and dBm.
That is our output power, yes. That's why we use decibels. And of course, dBms are just decibels to the ratio of 1 milliwatt, aren't they?
Yes.
So if we have 40 dBm input, we add 40 to it, gives me 80 dBm output. So easy to calculate.
But dBm in milli here.
Well, if you're going to change this to watts or milliwatts,
No,
Right.
dBm and dB. It's not different. This is with milli and this.
remember that dBs is a ratio of power. dBm is a ratio to 1 milliwatt.
Yes.
Okay? So all you have to do, if you've already got your power in dBm, is just add the dBs or subtract the dBs, depending on what you're doing. So we begin with 40, add 100, minus 60, 80. Do you agree with that?
In watts.
In dBms.
If it's
If it's in watts, you then can get the output, the final output, and change this to watts. Okay?
no, if the power input is in watts.
Oh, if the power input is in watts, then it's a different calculation altogether, isn't it? You have to then find out the power ratio here,
In watts.
and then the output power in watts. And you can change that to dBm if you wish. But you see, if your input is in dBm, and your gain is in dBs, then, and the output is dBm,
If you
no
ask,
need to change them.
He asked about the output dB. Also the same answer. The output dB you want.
There's no such thing as output in dB. That's impossible. You can have an output in dBm, or you can have an output in power as watts. You can't have output dBs. dBs is a ratio. dBm is a power. So either the output is in dBm, or the output is in watts. Now the second example here,
Minus 10. No, it's
you told me you can't have a minus watts.
What هذه يا الشباب؟
Anyway, before we do the second example, do you understand what we did here? Once you've got everything in as a logarithm,
But I confused about dB and dBm. This is a reference to the milli.
okay, all right, let me put it this way. If I have 1 milliwatt at the input here, right, and I have a little amplifier here of 40 dB, the output is 40 dBm. Because I'm increasing the power, right, increasing the power of 1 milliwatt by 40 dBs. So if I have 1 milliwatt here, 40 dBs here, 40 dBs here gives me a total of 80 dBs, doesn't it? Do you agree with that?
Yeah.
A gain of 80 dBs
Yes.
on 1 milliwatt. So the output in dBm is 80 divided by 1 milliwatt, which is 80
So that,
dBm.
not multiply, it is adding.
That's right. Once you're dealing with dBm and you're dealing with dBs,
Subtract
you
it.
add and subtract.
That's,
Which brings us to another advantage of using dBs, doesn't it?
it is easy.
It is easier in that sense. So if you've got an input power in dBm and you're asked for an output power in dBm, then of course just do your adding and subtracting, right? And then you end up with 80 dBm. Now if you wanted to, you can change this to watts. But it's not necessary. If it's watts, it's 10 to the power 8 milliwatts, which is 100 kilowatts.
How can I change it to
Right, what's 80 dBm? Well, in fact, we're going to do that here. Right? That's 10 to the power 8, isn't it? Right? Over, or multiplied by, 1 milliwatt. We're doing it the other way around. That's 100 million milliwatts. Now, milliwatt, of course, is 10 to the minus 3, isn't it? So this comes to 10 to the power 5 watts, which is 10, sorry, it's 100 kilowatts. If that's what you wanted to do.
We wanted the what?
That's if you wanted watts, yes. But I didn't ask that question. Don't have to do this. That's the answer, 80 dBm. I'll tell you what I'll do with the second question. I'll leave this second question on the board. I'll put 2 other questions on, and then we'll go through them on Saturday. Okay? Because I don't want to rush this. This is important, you know. But I want you to think about it over the weekend as to what. Okay, so I'll leave you with that. So we'll do that on Saturday then. Now, the first thing we talked about was decibels as a measurement of ratio of power, and then we mentioned dBm as a measurement of power. And then I left a couple of questions. This question I actually went through with you on Wednesday, question number 1. And question number 2 I asked you to do yourselves before today. So let's go through some of these questions and see how we get on. First of all, if we have a look at question number 1 that I completed on Wednesday, we'll see the advantages of using dBs and dBm. Here I have an input power. Now when you see dBm with the small m, that means it's a power measurement. If it was just dB, it's a power ratio. So that doesn't, dBs itself doesn't tell you what power it is, dBm tells you the power. Now we have an input power here of minus 10 dBm. Yes. Okay. When you see the minus sign, what does that tell you? No, this is a measurement of power. This is not a power ratio, this is a measurement of power. I meant, what does it mean when you see it in front of a dBm?
The definition here is just say the dB is the ratio of power.
Yes. What I'm saying here, though, is in dBm, what does the minus sign tell you?
Lose.
No, dBm is a measure of power. There's no such thing as loss, or it is an absolute measure of power. So what does the minus sign tell you? Can you get such a thing as negative power?
Less than 1.
Yes, that's exactly what it means. It means the power is less than 1 milliwatt. Remember, everything is referenced to 1 milliwatt.
Yes.
Okay, so if you get minus 10 dBm, for example, as you say, Abdul, if you get minus 10 dBm, anything negative, when we're talking about dBm, it means less than 1 milliwatt. It doesn't mean to say a negative power, of course. There's no such thing. All powers are positive power. It can be very small, but it is a positive number. So you must always remember this. And this, of course, is the feature of using logarithms. This is a logarithmic measure of power. dBs are a logarithmic ratio of powers. Now we start with minus 10 dBm. Then we go through an amplifier. Okay. And the amplifier has a gain of 40 dBs. Then we go through an attenuator with a gain of minus 40 dBs. Well, if you already have your power in dBm, then all we need to do, if this was a power ratio, then we would have to multiply this gain by the input. And if this was a power ratio, we would have to divide it, right? But because we're already dealing with logarithms, we just add and subtract. So for example, a plus 40 dB gain and a minus 40 dB gain, they cancel more or less. whatever the amplifier is supplying, the attenuator is attenuating. So we end up here with the same as we begin with. So basically the output is the same as the input, minus 10 dBm. So the object of this exercise really is to calculate what the output power is in watts, or milliwatts, or microwatts, or whatever. Though I've given you the power in dBm, you need to change it to watts, or milliwatts. Well, remember the formula that dBm is equal to the log of the power over 1 milliwatt multiplied by 10. Therefore, dBm over 10 must equal this. Now, dBm is minus 10. That's what we're told. Just rearranging this formula, dividing both sides by 10. Therefore, dBm over 10 must equal this. And of course, 10 over 10 is 1, so it's minus 1.
Yes.
So what's saying is that the logarithm of this ratio is equal to minus 1. Or putting it another way, from our knowledge of logarithms, which you should already know, 10 to the power minus 1 must equal this ratio, mustn't it? It's just a rearrangement of this formula. So 10 to the power minus 1 is equal to the power over 1 milliwatt. Therefore, the power must equal 1 milliwatt times 10 to the minus 1. 10 to the minus 1 is a tenth, of course, isn't it? 1 over 10. So 1 divided by 10 is 0.1. So the answer to the problem, the whole question, is 0.1 milliwatts. Or you could say 100 microwatts. That's not, you put it any way you wish, but that's the answer. Okay. And that's what we did on Wednesday. We went through the solution on Wednesday. The second question I left you with, though, the one that I wanted you to work out over the weekend, question number 2, is like 2 or 3 questions all in one. That's just an example. We begin again with a certain value of power input. Then we attenuate the power, amplify it, attenuate it, amplify it, and then see what the output is. It's nothing more difficult. It's just take each stage at a time, consider it like a separate little question in each stage, and you should end up with the right answer. Now, the first question here that I'm asking is, what is the gain of this attenuator D? What is the gain of that attenuator? Now, you can talk about the gain of an attenuator just as you can speak about the gain of an amplifier, except that if it's in logarithms, it'll be a negative number, won't it? Because the output is less than the input. Yeah, so it's going to be a negative number. Well, we begin here. You see, I've made it quite easy. I haven't put a power input and output here in terms of watts. I've put it in terms of dBm. So now it should be much easier to see what the gain of this attenuator is. We begin with minus 20 dBm, and here we have minus 30 dBm, so it must be minus 10, mustn't it? It's a straight addition. Minus 20 plus minus 10 is minus 30, so this must be minus 10. There's no calculation, or not much calculation involved in that question. So the answer to A is minus 10 dBs. In other words, the ratio between output and input expressed in dBs is minus 10. If I had have asked this same question, what is the gain of the attenuator, and this figure here, instead of being minus 30, was, say, let's say minus 10, what would be wrong with that question? It wouldn't be an attenuator, exactly. This has to be more negative than this. That's right. It would be an amplifier, that's right. This has to be more negative if this is an attenuator. Yes. Isn't it? In fact, I needn't even have told you that was an attenuator. I could have just said, this is something, what is it, and what's its gain? You would then guess that it must be an attenuator, because this is less than this, more negative than this. It had to be an attenuator. And the answer to the problem here is minus 10 dBs as its attenuation. Okay. Okay, now, so this is our signal here, and now it's saying, what is the signal here? What is the power of the signal here? Okay, what is the power at A in dBm? Again, we're sticking with dBm, so it makes it much easier. We don't have to change it to watts yet. Well, we begin with minus 30 dBm, then we go through an amplifier of 100 dBs. So what is the power here? 70
dBm.
dBm, yeah, exactly. Begin here, minus 30 plus 100 gives us plus 70 dBm. Then we go through an attenuator of minus 40 dBs. So we begin with 70, it's like 70 into the attenuator, minus 40.
Minus plus 30.
Plus 30, yes, of course. dBm. Did everybody get that answer? Or anybody not get that answer and not understand why? Basically, we begin with minus 30 plus 100 is plus 70, minus 40 plus 30. So here would be 30 dBm a day.
Plus 70 minus 40?
That's exactly it. Plus 100 minus 40. Well, yes, here it's plus 70
Yeah.
minus 40. The gain of these two together is 60, isn't it?
Yes.
100 minus 40 is 60. So you can say minus 30 plus 60 if you wish, the same answer.
Yes.
Plus 30. Now you don't really need the plus sign here. If you didn't have the plus sign, it's assumed it's positive. But put it in, you know, to remind you that it is a positive number. It's always a good idea to put that in so that you know what it is. Now we have the power at A, and what is going to be the power at B? Well, it's quite straightforward now. We've got plus 30, minus 20, 10. That's right. Don't forget it's still plus at the moment, plus 10 dBm. So that's here. Okay, now we want the answer at C. This is becoming a little bit like question 1 now, because we want the answer in watts or milliwatts or microwatts, whatever it is, or even kilowatts, whatever it is we've got. We know the B is 10 dBm. The gain is 20. So what's C in dBm?
Yeah.
30.
30 dBm. That's right. 30 dBm is the power at C. Right. But what we've got to do here, we've got to find that in watts. So we've got to use our same formula that we had down here. So using this formula, dBm over 10, which is equal to 30 divided by 10, which is plus 3. Over 1 milliwatt. Therefore, 10 to the power 3 is equal to that ratio, isn't it? Do you agree with that? So what is going to be the power?
1 watt.
1 watt. Remember, it's a power over 1 milliwatt. Remember, the ratio is over 1 milliwatt in dBm. So, if we rearrange that, we can say, therefore, the power, bringing this over to here, is 1 milliwatt multiplied by 10 to the power 3. which is 1 watt. 1 watt. Fahad, did you get these answers?
Yes.
And the final answer here, 1 watt.
This is the power.
Power. Now we use decibels and we use dBms, you know, not just in amplifiers and attenuators. As we'll see in a minute, we also use it in antennas, measurement, what we call antenna gain. I'll come to you in a minute. We use it in modems, telephone circuits, data circuits, anything that requires signals in communication. All communication systems will require the use of dBs and dBms. So we need to be quite familiar with that. We shouldn't be getting too many difficult problems. The one I want you to remember, of course you should know what whole powers are, 10 to the power 1, 10 to the power 2, 10 to the minus 1. You must know what those ratios are. They're quite easy, they're whole numbers. The only other one you really need to remember is times 2. Now that's between 1 and 10. Well, 1, remember, is 10 to the power 0, isn't it?
Yes.
And 10 is 10 to the power 1. So the number 2 is between those two, isn't it?
Yes.
So it's going to be above 0, but less than 1. And in fact, you can show it that if you multiply by 2, it is in fact 10 to the power 0.3 something. You've got, has anybody got a calculator with the logarithms on it today? Because if you have, and you say 2 and the logarithm of 2, the antipod I should say, 10 to the power 0.3010 something. 299995, yes. We take it as just 0.3 as a quick one. That's the one I'd like you to remember, because we will be using this. If you multiply something by 2, the logarithm is 0.3. Multiply something by 1, the logarithm is 0. So for example, if you have an attenuator or an amplifier where the input and output is the same, there's 0 gain. It's not increase, it's not decrease, it's the same. 0 gain. And of course times 10, 10 to the power 1. 100, 10 to the power 2, and so on and so forth. The only other thing you remember, of course, is you can combine these. So if I multiplied something by 20, that's the same as adding the 2 logarithms, isn't it?
Yes.
It's the same as 10 to the power 0.3 plus 10 to the power 1, isn't it?
Yes.
And so the logarithm, 1.3, so the logarithm of that number would be 1.3. And the decibels, 10 times that, because we always multiply the result by 10. It would be 13 dBs. If something's multiplied by 20, it's a 13 dB gain. That's what we say in that example. We might do a few more examples like that later when we get some more practical examples. I don't like to just do the theory without some practical implications, so we'll wait till we get a little bit more practice on that. But we will come back to decibels quite a lot. Are there any questions about this particular example that I left you with? Do you understand how we got these answers? Particularly this final one, same as we did on Wednesday with our 0.1 milliwatts. If you have the calculator, of course, you can work out any ratio, but even without that, if you remember the times 2 is 0.3, and remember your basic theory for logarithms, then you shouldn't probably need a calculator. And in an examination, you wouldn't need a calculator actually, but you can use it if you wish. Okay, let me erase this then. Talked about yesterday about the range of radio signals. somebody asked, what is the range of a radio wave? And of course, we're concentrating in this course mainly on these bands, VHF, UHF, and SHF. Those are our three main bands that we're dealing with. Basically, the higher UHF and the SHF band, we can call the microwave band. These are our three main bands of frequencies that we're going to use for communication. And essentially, in all three bands, the range over which you can communicate depends on the distance between the two transmitter and receiver antennas and the height of the antennas above the ground. I'm going to give you a little formula which I found over the weekend, which might help you to understand this. So you can take this little drawing down. It will help you to follow what we mean by the range at these frequencies. If you imagine this is the curvature of the Earth, because basically we're limited to the horizon. You know, if you go below the horizon, you lose it. And I'm assuming there's nothing between. Either we're in the middle of the ocean or in the middle of the desert. There's no hills, there's no buildings, completely flat. Then, if this is our, say, transmitter antenna, just draw a little dipole like that, then basically it transmits in a straight line, and this is our receiving antenna here. Like that. This is supposed to be a straight line between them, which just touches the horizon. This is the maximum theoretical range, call that the range, of our signal. It doesn't matter which way we take it, either one can be the transmitter or the receiver. And if I say that this here is the height, let's call this the TX height, TXH, and this one is the RX height, in meters, then we can derive a little formula actually, which I derived over the weekend, as to the maximum range. And it's this. Sorry? Height. Yeah, this is the height above the ground of the particular antenna. And that's the formula which we can use. Let me just say it in words what we have here. 3570 multiplied by the height of the transmitter routed plus the height of the receiver antenna routed. So I'll just put down here what it all means. The range is in meters. Spell it the French way. And the height, TXH, height of TX antenna above ground. And RXH, height of receiver antenna above the ground. And you can calculate very, very close this, at least to the nearest meter, what the range is between your transmitter and receiver. We'll do a couple of examples of this to give you some practical. This is meant to be a dead straight line, of course, between the two.
Square root of TX height
and RX height, yes, that's exactly. Distance between the two, you lose your signal because of the horizon, don't you? So it's the maximum theoretical range, and of course if there's anything situated between the two, you're going to perhaps lose your signal depending on what's there. This is maximum.
TX another? Or what?
TXH and RXH.
Engine?
Height?
Antenna?
Antenna, yes.
Above? Ground.
Above ground.
That's a amount of range between the two antennas.
That's the range between the two antennas. The range of your transmitter to your receiver.
The airport, the airplane will connect to the tower, VHF.
Yes, it won't use HF. You mean you're talking about the air traffic control range? I'm not sure. I think it uses VHF, or it could use UHF.
No, because when they fly this shut off all the mobile, because the mobile also VHF.
The mobiles that we use are UHF actually. Yes, or maybe it's UHF that they might use then. It used to be VHF, maybe it's changed to UHF because we're using UHF for the mobile.
Mobile is more than
Walkie-talkies, I think it's UHF. Even if you're considering light waves, it works the same way. For example, if you're in an open space, traveling in a car, say, there's your car, in an open space, the question is how far can you see to the horizon, looking straight? Now, assuming there's nothing there, the distance you can see depends on the height of your eyes, in that case, above the ground. And assuming that you're looking at the horizon itself, basically what this formula says, we're taking this distance from the transmitter to the horizon and adding it to this distance. That's what we're doing. But if you were in a car and you wanted to see how far you could see to the horizon, then you've got to take your height above the ground. Well, your height was what, about a meter when you're sitting in your car above the ground? Approximately 1 meter. So what's the root of 1? 1 multiplied by 3,570. So you can see approximately 3.57 kilometers to the horizon.
The height of transmitter is 1 received.
I'm talking now in a car, you don't have a receiver, you're just looking to the horizon. You're not looking any further than that. There's nothing here you want to look at, just to the horizon. If you've got another car here, and that's about 1 meter, slightly more in fact, then you double that. It's twice that much. You could see another car about 6 or 7 kilometers away. I'm not taking into account anything, any mirage or any effect of the heat or anything, just straight, in a straight line.
Square of 1 is 1.
Yes, if this is 0, then it's 1 times this, isn't it? If this is also 1, then it's 2 times this. So roughly twice that distance if there's another car you want to see. Approximately.
3,570 meters, I guess.
3.57 kilometers, yes. Yeah. That's right.
How long?
Not that long. If both of you are doing 80 kilometers an hour towards one another, you're approaching at 160 kilometers an hour. You soon pass one another. Assuming a dead straight road, you know, no. Let's do an example then for a radio. What do you think the height of the antenna is above this building? Above the ground? Above the ground is what we're interested in. You're saying 20 meters above the sea, above the actual roof. Okay, well, how high is the roof, do you think, then?
8 floors,
It's about 8 floors, isn't it? 9 floors, actually, yes. There's a 9th floor, which is got the air conditioning and everything and the water sprinkler system. So you got 9. And how high is each of these floors? About 4 meters? Well, I'm 2 meters. This is a false ceiling, by the way. If I open this,
4 meters.
you've got quite a height above here with all the pipes and everything. So let's say about 4 meters, including the thickness of the concrete and everything between our floors or whatever we've got. So if we say 8 times 4 is 32. Sorry, 9 times 4, 36. And then you say 20 meters on top of that, that's 56 meters, isn't it? Okay, so let's say the transmitter height then is 56 meters. That's the height between the ground and the actual antenna itself. Now, how far can you see with that? Well, that depends on the height of the receiving antenna. No, you shouldn't have to. It can be anything. But if the receiving antenna is a car, it's going to be about 1 meter, isn't it? So let's say we have just 1 meter high. That's a car. That's 1 meter. So we're communicating between our antenna and a vehicle. Okay. Putting in this formula then, it's 3570 times the root of 56 plus the root of 1, which is just 1, of course, isn't it? All right, those with the calculator. What is the root of 56?
7.48.
7.48, and we'll add 1 to it. 8.48. And what's 8.48 times 3570?
30.27.
30.285.
Okay, well, and that's in kilometers, right? Thousands of meters. About 30 kilometers. 30 kilometers.
That's almost in one.
Well, of course, yes, almost to the airport, and that's for vehicle. Now, at the airport, if we want a point-to-point communication, then we're actually communicating with a fixed antenna at the airport, which is mounted on top of the building. So the height is more than 1 meter, isn't it? I'm not quite sure. Maybe another maybe 30 meters above the ground. I don't know what the height would be. So you would have, in this second part here, instead of root 1, it would be the root of, say, 20 or 30. Okay, so you add that to our original 7.48, and then you end up multiplying it by 3570. You'll get a lot more than 30 kilometers. About 46 kilometers or something. Point-to-point distance, yes, between this antenna and the antenna at the receiver or transmitter.
There is a problem. This it's not
So can the rest of you just keep quiet a minute, please, while I just listen to what Khalid's got to say.
This 30 kilo, this distance or what?
The distance between the transmitter and receiver.
The receiver, you said, this vehicle is mobile.
That's right, yes.
Even here.
So that's its maximum distance, you see, isn't it? Yes.
But that car maybe will be in the airport. The same.
Now, what we're saying
The
is,
same height, one meter.
well, yeah, what we're saying is that the maximum distance, this 30 kilometers we calculated here, is the maximum range between our antenna and a car, for example, with just one height above the ground, 1 meter height. Now that car can be anything up to a maximum of 30 kilometers.
maximum.
maximum. Anything more than that, we might lose it. That's what we're saying. If it's closer, no problem, because your transmitter is transmitting, remember, in, you know, it's going to cover the whole of this range.
Will be cut the communication between.
Yeah, that's right. If it goes further than that, goes over the horizon, that's essentially what's happening.
It's مدى
Yes, you were saying, Khalid, yeah?
mount an antenna that goes to house.
Yes.
It's nothing more than a house, so you can imagine something about 7 meters.
Yes.
It can reach up to 300 kilometers.
No, it won't. No.
Well, I did it by myself.
It must do. Are you talking about a cellular phone?
No, it's not a cellular phone, a mobile phone.
A mobile phone? What type of mobile phone?
See now. It was mounted in Yambo and I was speaking in Jeddah.
Well, if that's the case, and there's no repeater,
No repeater.
then it must be a strange phenomenon. It's not normal. It would not be normal.
Yalla.
Yeah, would not be normal.
It's strange in a straight line to the, let's say, an airplane, not on the horizon.
You weren't in an airplane then?
No, I wasn't on the ground. It reached to up to 400 kilometers. But on the day, now, it reached to 600.
Yeah.
Open area.
It doesn't matter about the area. No, it's wrong. It's wrong. It cannot be right. Cannot be right. There must be something, either reflection or repeating or something, but it is not the normal. You couldn't, it's in theory, well, I'm assuming you're using something above VHF. You must be using. You must be using. Probably UHF, I would think UHF. So if you did get that sort of range, it must be something else. We'd have to see the experiment properly. But I'll tell you now, no radio guy would ever agree with that. Theoretically, that cannot be. 600 kilometers, you say?
Above the ground.
600 kilometers above the ground?
Yeah.
No, it's
And 400 on the ground.
No, I know what you mean. You mean you're talking about the range here being 400 kilometers?
Yes. And the range above?
Well, above the ground is different because that's in a plane, isn't it?
Yeah.
But I'm talking about straight point to point. Straight point to point.
400.
I can't see that. I mean, we can hardly get to the airport here, let alone 400 kilometers.
Should be submitted as not.
There can be some freak conditions which cause the wave to bend, but we can't rely on this necessarily.
That's mobile number. If I see maybe with the.
It could be a reflection. Yes, that can happen. That can happen. You can get what is known as tropospheric scatter. Yes. And maybe that would be the reason why he's got that distance. Because it seems to be clear that 400 kilometers is over here somewhere, right?
Yeah.
Now, there is such a thing as tropospheric scatter, which I wasn't going to mention, but as you know, above the atmosphere, you've got an area called the troposphere.
Yeah.
yes.
Now, under certain conditions, it's possible for this wave to hit the troposphere, and a little bit like I was mentioning about the HF situation, the wave can get bent. It actually reflects off the troposphere like this. Under those conditions, you can receive, obviously a lot further than the line of sight, but it's not something you could rely on totally. I would think it would change throughout the daytime and nighttime, whether you could, you couldn't sort of say guaranteed all the time. Now it's different if you take an aircraft, because with an aircraft, of course, it's flying much higher anyway. So if for instance, we wanted to know the range of an aircraft, the height that we take for the transmitter would be, what, 30,000 feet, isn't it? Say 10 kilometers, 10,000 meters. So here, it would be the root of 10,000, which is 100. So an aircraft would be 357 kilometers to the horizon. To the horizon. But that is a special case, of course, with an aircraft. I've even heard people say that New York taxi drivers talking to one another could be heard in London through this tropospheric scatter. They're using VHF.
It's from France to Turkey.
No, nothing to do with aircraft. Troposphere. Way above the aircraft. Yeah, it's way above it. There's even been stories of that. At certain times of the day, you could hear these taxi drivers talking to one another.
Maybe humidity.
It does depend on weather to a certain extent. There are actually special antenna systems that can be built to make use of this, called stratospheric communication systems, rather complex antenna systems which make use of it, which tend to make it a little bit more reliable. But what I'm saying is that if you do get a distance like that, it is due to some sort of freak condition. Freak meaning unusual, not everyday reliability. Because even here we have difficulty getting the range we already have. Of course, this doesn't tell you your coverage. I mean, this just tells you your theoretical range. If you're on UHF, for example, remember what happens when a wave hits the building. Some of it will be reflected, a lot of it will be absorbed at UHF, very little gets through. So although you might be able to talk to a car 30 kilometers away, a car a few streets down here, just a kilometer or two away, you might not be able to talk to because of the buildings in between. So it doesn't necessarily give you all the answers. You've got to consider coverage as well. But to answer your question, Khalid, the only thing I can think of is you've got some probably stratospheric scatter that's causing this condition. If you did hear the signal from that distance, and I would guess that the frequencies are UHF, or that you're using for that mobile, I would guess.
So the stratosphere can reflect VHF?
It can, well, it can do. It can reflect VHF and UHF. It's probably unlikely to have any effect on SHF. It doesn't have
Maybe the
effect.
friend of Khalid is installed a repeater
Without telling him it. No, it probably can happen under those conditions, but I wouldn't necessarily say it's reliable 24 hours a day.
The problem is from your point
The distance covered by sea, isn't there? That that also can make it. You can get you can get this sort of action. I'll tell you what you can do in stratospheric scatter. Basically, what happens is this: the wave goes up, bounced by the stratosphere, back to the ground, it goes up again, bounced, and like that. Okay? That's what's happening in stratospheric scatter. It works better over the sea, because you get better reflection. Okay? Also, you might be able to hear it in Jeddah, but if you were somewhere in between, you might not be able to hear it, because it just so happens it bounced right over you at that particular point where you were. That can happen.
there is a solution for it to change the power of transmission.
Direction as well makes a difference. They make special antennas to make use of the stratosphere. The direction at which you launch the wave can be critical as well. That's another thing. The angle, yes, that's right. Yeah. Rely on. But it can happen. Applies, of course, also to microwave point-to-point link. Okay? It applies equally to microwave point-to-point link. So if you had a microwave dish, then again the maximum you can expect to get reliably on a point-to-point, one microwave dish to the other would be this, according to this formula, exactly the same. Also at microwaves, you're usually dealing with the SHF frequencies, less likely to be affected by the stratosphere. You certainly wouldn't get much more than as we know, microwaves are also used for satellite communications. So in other words, if I was to point the dish up to the sky, I would expect the microwave to go through the atmosphere and the troposphere and the ionosphere, not to be reflected or distorted in any way. And that's true for microwaves to a certain extent. Let's consider for a moment microwaves. Remember last week we said if you wanted, say, a set of telephone lines between here and another of your buildings somewhere, a cheap option may be to put a microwave link instead of burying cables in the ground. More convenient to just mount your microwave on top of your building. But, of course, it's not without its disadvantages as well. So if we consider two dishes, and we're considering communication between those 2 points. First of all, yes, any problem, please?
Yes.
Yeah.
So you said before, if you are in a car, the maximum distance you can see is 3 kilometers.
About 3.7 kilometers to the horizon. Yeah.
To the horizon. Nothing more than that.
That's assuming no other reflections or, images or anything like that. Just normal, straight. Yes.
So if there is abnormal conditions, it would be much less.
Oh well, I mean, if it's like sandy or raining or something like that, it's going to be less.
So
But I'm saying like a clear conditions. Yes, clear
There is
conditions.
nothing more than that you can see more.
You will see more if what you're looking at is higher than the ground. Like another car, for instance, double that distance, won't it?
Depends on the height.
It depends on the height, exactly. If all you're talking about is two vehicles, and we say that the height above the ground of one vehicle is about 1 meter, then it's about 3.7, isn't it? 3.57 kilometers to here, to the horizon.
Before all days, there was this lady who would see the.
I'm not talking about the mirage now. I'm not talking about the heat.
She would see the camera coming 3 days ahead. And you can imagine 3 days ahead.
What's coming 3 days ahead?
How do you calculate the 3.70?
It's to do with... We'll have a break in a minute. Before we do, let me just mention this. So we have a point-to-point microwave dish. Now, we did say that the frequencies used by microwaves, of course, are probably in the SHF band. So what sort of wavelength are we talking about? Meters? Tenths of a meter? Centimeters, yes. We're dealing with very small wavelengths, aren't we? That's why we can use smaller dishes, right, to get our beams between one antenna and the other. The idea being it's a point-to-point, so we must be able to see each antenna from each other of the other antenna. We know that if somebody was to build a big building in the middle, we've lost our communication. Unless we do something else about it, we can't rely on that communication. So it's important to remember this. But there is one other little thing which perhaps we should consider, particularly in our situation, and that is, what about dust or sand and also rain? This is probably less common, but it does indeed, yes. It does indeed. Particularly rain, more so than dust, in fact. It's all to do with the size of the particles, the physical size of the particles that are going to exist between your transmitter and receiver. And they're going to be, the size of those particles that are going to affect your communication depends on the wavelength. So some raindrops are big raindrops, some raindrops are small. There's different types of rain, isn't it? More like a drizzly small raindrop, and then there's the big heavy ones. Then of course you get the hailstone with the big blocks of ice or whatever, which is an extreme case. Raindrop size is important. The type of rain that falls. The manufacturers of the microwave system choose a frequency with a wavelength so that it's basically should be unaffected by most types of rain. But occasionally, as those of you in the radio department would probably know, occasionally you can get a rain shower where the raindrops are of a size which unfortunately make a big difference to the transmission, and you lose your link for the period of the time it's raining.
Lose it or affect it?
Sorry?
Lose it, lose the signal?
Yes, lose it, because the microwave transmission is bounced off each raindrop. Before it gets to the other end, there's so many reflections from raindrops, you cannot see it. In other words, this does not reach.
Then in rain, they stop using it.
Well, they don't have to, it'll stop itself. But they can't rely on it, that's true, under certain rain.
Place that always rain. They don't use.
Right, well, under a place where it's always raining, they would have to, the manufacturer of the microwave would probably choose a different wavelength in order to overcome that problem. Now, whoever chose the wavelength for us to use might be something to do with, we're more likely to be troubled with dust than we are with rain. This is less common, this is perhaps more common. Now, dust particles are much smaller than rain, tiny little particles, compared to raindrops, usually. And the microwave length is chosen so that the dust particles do not affect the wave very much at all, or shouldn't affect it very much. I don't know if it ever goes off under a very strong dust storm. Maybe it might do. But usually it shouldn't affect it. So that's how we've chosen, or the manufacturer's chosen the wavelength for us. If the rain is a fine rain, not very heavy, then again, not a big problem. But on the heavy rain fall, it can go off. But I think it does go off most of the time on the very heavy rainfall. You'll lose the communication during the period of time it's raining. When it's finished, it should go back to normal again, or should do.
What about the weather is windy? Strong?
Now, wind in itself doesn't affect the microwaves. But what the wind will do is move the dish a little bit. Now, that is a serious thing, of course.
Yes,
If it physically moves the dish, and it doesn't have to move it very much, only a very small. That's right. You see, if you only move the dish even by a small fraction of a degree, you can be way off, you know, you're pointing your beam way off from the receiver, and you can lose the signal that way.
Means that the wind is just effect on the dish.
On the
not
dish.
in the signal.
Not on the signal itself. It doesn't affect the signal. The wind has no effect on that.
Signal? Dust.
The dust should not affect the signal. At the frequencies we're using, the dust should have no effect. Neither should the rain, but unfortunately on the very heavy downpours, where the raindrops are quite large,
Yeah, sure.
it does seem to affect us. It does seem the problem of rain, well, we don't have much of a choice. We have to use the frequencies that we've got. We just have to put up with it. Every time it rains, we lose the link.
And the dust will not affect
Shouldn't affect it.
at all.
But I'm not so sure. Sometimes you can get some very, very severe dust storms where literally, you know, it's very... It depends on the type of dust. Most of the times I've not found it affects.
Just strong rain.
Strong rain will affect it. And the only time wind will affect it is if the wind actually moves the antenna a bit. Which can happen, of course. Possible. But otherwise, shouldn't affect it.
هذا نجيم بيتعدل 7 4 5 شهور.
In most of the examples I've chosen in describing antenna propagation, that is the way the wave travels from one antenna to another, I've assumed a dipole antenna. Now, with a dipole antenna, what can we say about the radiation from the dipole? Yes.
All directions.
All directions, yes. What we call omnidirectional, isn't it? Think of it as an omnidirectional. Now, okay, so if I have a dipole, we transmit in all directions, like that. So a dipole is omnidirectional. Now let's compare that with an antenna which is directional. A Yagi is an example. A dish is a very good example because it's even more. But let's say a Yagi. With the Yagi, remember, we got a polar diagram. Remember the polar diagram? Something a little bit like this. Right. Where this is the center of our diagram. Direction in this direction. This was an example of a Yagi. And of course this is directional. Right? Okay, now, without putting any figures in here or anything for the moment, let's say I want to communicate from this position here to somebody some distance away. Within the range, that is, not over the horizon, but within the range, let's say no buildings in between or anything like that. And I use a certain power of transmitter. Okay, now I'm just going to make up a figure here. You don't need to write this down, this is just an example. Let's say I'm using a 100-watt transmitter. Okay, so we have a 100 watts of power radiated in my omnidirectional aerial. That is in my dipole. And I have a receiver over here, some distance away, which is going to receive a certain signal strength. How strong that signal is depends on a number of factors. The main factor is the distance, isn't it? Okay, because remember, the further away you get from the transmitter, the weaker and weaker your signal is going to be. The question is this a problem? Okay, well, why can't I just say, well, all right, if I want to have a long distance, why don't I just make the receiver gain very high? Remember, the signal is going to get less and less. So I could say to myself, well, no problem with that. All I'll do is design a receiver with a very high gain to make up for the loss, you know, the weak signal. Do you think that would be a solution? There's a yes and no answer to this.
Yes, because your sister.
Okay. So, all right. So what you're saying is I can make this distance anything I like as long as
High gain?
I make this a very high gain. But is there any disadvantage here? Do we, you know?
If you make
Yeah.
it far of the...
If it's very small, if the gain of the transmitter is very small, sometimes...
You mean the power output from the transmitter?
Sometimes you can lose the signal.
How do you lose it?
It can be reflected. It can...
Well, all right. I know we can talk about reflections and everything, but let's say I have, let me go back to my original problem, a 100-watt transmitter. Some distance away I have a receiver, okay, with a certain gain, and I can receive the signal. No problem. Now what I'm saying is if I move this receiver further and further away, assuming I don't go over the horizon, of course, still within sight, we expect the signal to get weaker, less and less and less. Right, now I can say, okay, well that's no problem. All I have to do is make the gain of the receiver bigger and bigger, just add more amplifiers. See? Like if I have an amplifier and it has a gain of, say, I don't know, let's say 30 dBs.
You get much more noise.
Ah, now we're bringing, that's the word I wanted you to use. The word is noise, isn't it? Remember, we're dealing with radio signals here, and it's important that we can receive the radio signal above any noise. So if at the receiver antenna here I get a weaker and weaker and weaker signal, eventually, remember noise is generated all the time in any communication system, and radio is no different. Eventually the signal will go below the level of the noise. And it doesn't matter how much gain I have here, I can have hundreds and thousands of decibels. It's not going to help, because all I'm going to do is amplify all the noise and the signal. Do you see the problem?
The noise may be higher than the signal.
Yes. So what I'm saying is, the further away I make the receiver, okay, the less the signal strength is at the receiver. But of course the noise generated, that's going to be the same. So eventually the signal is going to go below the level of the noise. Remember? If we draw a graph here, and in green I represent this as the noise, now my signal, the transmitted signal, should be above the level of the noise, shouldn't it? So we can receive it.
Yes.
But what happens as I go further and further away, this signal gets less and less, and eventually could be below the level of the noise and basically lost.
When you generate
Well,
refer the signal.
yeah, the point is, I'm just talking about a point-to-point now, no amplifiers in between, no regenerators or anything like that. So there is a limit to how far away I can. Also, if we take the power of the transmitter, this 100-watt transmitter, okay, I have a certain power here, I'll receive a certain signal here. Let's say the signal here is 1 microwatt of power. Right, 1 microwatt of power. I'm only choosing that as an example. But so I have a 100-watt transmitter, but by the time the signal has reached the receiver, because it's spread, don't forget, in all directions in this example.
Yes.
We're spreading it behind, above, below. Most of it, as you can imagine, is wasted,
Yes.
isn't it? Particularly on a point-to-point. So by the time it gets to the receiver, we might only have 1 microwatt of power to induce a signal into the receiver. Now let's say that's okay, but if I reduce the power of my transmitter to say 10 watts, then we expect this to go down, don't we?
Yes.
And eventually it could go below the level of the noise. Okay, now there's one example, using a dipole, omnidirectional antenna. We would probably have to use a dipole, or at least a stacked array, if we were communicating on a mobile basis, because the receiver could be anywhere around the antennas.
Cover an area.
Yeah, we would have to make it at least omnidirectional in the azimuth anyway, at least in the horizontal.
So, excuse me, when we want to speak about the range of how distance you want to transmit, it's the last distance, the noise.
Yes. Now here's where we're bringing into account noise. Before, remember when we spoke about the line of sight for, that was just the maximum possible range according to the mechanics of your height of your antenna, curvature of the earth, etc. But now, of course, we see that there's a little bit more to it than that. If I make this signal too weak for this distance, then maybe this power here in the receiver is below the level of the noise that can be generated. And if it is, then it's not going to be sufficient. There is actually a calculation we can use to find out what this power is going to be. Now what I want to do now, I want to now consider the same situation, only using a directional antenna, a Yagi.
For point to point.
For point to point. Yes, of course, with a Yagi, with a directional, because it's directional, we're basically talking about point to point, aren't we? We wouldn't use this sort of antenna for mobile, for obvious reasons, because as the car goes around, or whatever it is we want to communicate with, it could be behind the antenna, and we're not going to get as much gain.
So for this cordless telephones at home, we are using a very small power so that it would only give no, it would
Are you cordless? You're not talking about cellular now, you're talking about cordless. Yes, it is only a low power, but they aren't omnidirectional.
It is a
It is omnidirectional. Because, for example, you could have a cordless phone downstairs in your house, and you need to go upstairs with your handset.
Yes.
So it needs to go up as well as around, doesn't it? So that really is omnidirectional. Don't have much choice on that, really.
Yeah, and it's a very low power. Because if you go outside the house, it will.
It could disappear altogether, yes.
And
It
if
is.
someone has got a similar telephone, he can speak on your line if he's in the house.
Well, I'm not so sure about the particular model you have. The newer, so it's not that new now, going for a few years, mobile or cordless telephones operate, I think, about 900 megahertz. I think it's 900 megahertz, the UHF band. And not only are they low powered, but they are encoded. There's a code. They're scrambled, in other words.
No, it changes its frequency time to time.
Well, no, wait a minute. Both can be correct. The later ones scramble. So that if somebody else next door has the same type of telephone you have, there are, I think, on the one I have anyway, 64 different scrambling codes. And it's chosen at random. The chances of the guy next door having the same code as you is pretty well, remote. But if he did have the same code and you happen to hear him and he could hear you, you can always change your scramble code so that you no longer can hear one another. There's that. That's not the same as interfering. You're still going to sort of interfere, but at least he can't hear from you. Now, to stop interference, the only thing you can do then is to use a different channel. And I think there are 2 or 3 channels, I'm not quite sure how many, depending on the phone, that you can use so as you don't interfere with one another. There's different techniques for cutting out that problem. But regarding range, yes, obviously the lower the power of your transmitter, the smaller your signal is going to be in your receiver. Now if we take a Yagi, which is a directional antenna, so this is a different situation. What do you think, if I apply the same power here to the Yagi, and I put my receiver in front of the Yagi in the same direction, do you think I'm going to get 1 microwatt or more than 1 microwatt? More. Yeah, indeed we are. It seems obvious that we're not wasting energy, too much energy anyway, radiating in the backwards direction. Most of it's going to come forward, so we would expect a higher power here. Let's say instead of 1 watt, I got 2 microwatts instead of 1 microwatt. Do you agree with that? Now, the exact figures we can talk about later, but let's say I got 2 microwatts instead of 1 microwatt in my receiver. Compare the Yagi, right, with a 100-watt transmitter, and the receiver's receiving 2 microwatts. Compare that with the previous example. Now, let's say in the previous example, I boost this power, I make the power bigger, so as to make this 2 microwatts, same as this. How much power would I need here? Yeah, 200 watts. So, using a different antenna, it appears to behave as though it's amplifying the signal. Instead of using 100, it's like an omnidirectional at 200 watts. We call this antenna gain. It's not actually amplifying the signal. What it's doing is not wasting it. That's basically what it's doing. But it appears as though it's the same thing as increasing the power of your transmitter compared to an omnidirectional antenna. Yes, technically, I'll put the definition down here. It's the signal strength at the receiver. Let me put it down, then you can see it clearly.
If you increase that power, you increase the gain, the antenna gain.
No, the antenna gain depends on the shape of your polar diagram. In other words, it depends on the type of antenna. Right? So if I was to use a Yagi instead of an omnidirectional, it's exactly the same thing as using an omnidirectional at a bigger power as far as the received signal is concerned. So we call that antenna gain. So technically it's a ratio of powers. Okay? I'll put down here the definition of what antenna gain is. Here's the definition. So it's a ratio of the signal strength you receive for your particular antenna compared to what you would receive if it was an omnidirectional antenna. So in this example, I would receive 1 microwatts if it was an omnidirectional, but for the same power here, 2 microwatts. So I get twice the power because I'm using a different type of antenna. I haven't changed the power of the transmitter, I've just changed the type of antenna I'm using. If by using a Yagi I get twice the power compared to using an omnidirectional, twice the power, then how many decibels is this? 3. 0.3 times 10. In other words, we say the antenna gain of the Yagi in this example would be 3 dBs. Normally the antenna gain is much more than 3 decibels. That's an example here where you've got twice as much power in your receiver compared to that from a omnidirectional.
3 dB as we mentioned last week.
Yes, we say the antenna gain is 3 decibels. This is where we talk about ratio, and then whenever we talk about ratio, we can express it in decibels. 10 log times the ratio times 10, and that will give me 3 decibels if it's twice the power, 3 dB.
500 watt from antenna or from
TX. That's the.
from antenna.
No, that's the power of the transmitter in that example. Say this is the transmitter, this is the receiver.
From antenna, how much?
That depends on the efficiency of the cabling and everything. I don't know what that'll be.
Much losing or
Sorry?
much losing?
There will be some loss. There'll be some loss. Not all antennas are 100% efficient. Depends on the cable connecting the antenna. Depends on the situation of the antenna, whether it's close to buildings or not, or whether it's out in the open. There's a lot of things depends on that, which is a little bit beyond this. I'm just taking this as a simple example. You can't. You just got to take the transmitter power. That's all. It won't be all of it radiated, but you can assume most of it will be. Does everybody?
What is the difference between different antennas? 0 dB, 3 dB, 6 dB?
Well, which antenna would have 0 dB gain?
0 dB? The one that 1 watt, I think.
No. What is?
It won't transmit nothing. It's
Nothing. Between them, nothing.
again.
By definition, if I said I have an antenna with 0 dB gain, what type of antenna is it? Remember, the antenna gain is nothing to do with power input and power output. It is to do with the shape of the dipolar diagram produced by the antenna. That's what it is.
0 dB?
Yeah, dipole, exactly.
0 dB?
Normal dipole.
A dipole has 0 dB gain because when we take the ratio of that power, 1 to 1. You're comparing it to a dipole. Well, if you're comparing a dipole to a dipole, it's 1 to 1. So it's 0 dB gain.
3, so that it is lambda.
It's now a comparison between a lot of things, like
No, all we're doing is comparing the signal strength from a dipole compared to that from a particular type of antenna.
the DBM is comparing.
No, not to mention about DBM.
No, it's also a comparison to 1 millivolt.
More milliwatt.
1
Yes.
milliwatt.
That's if you're measuring power itself.
Yeah.
Just power, yes. But here we're measuring just power ratio. In other words, I might not have 100 watts here. I might have much less than 100 watts. I'm going to get much less power here. I'm not actually measuring power. I'm measuring what it is compared to what I would get from a omnidirectional antenna. Okay? So if somebody says to you, you've got an antenna with a 0 dB as an example. If somebody says to you, I've got an antenna with a 0 dB gain, you know that the gain of that antenna, whatever shape it is the same as the gain, or the output from it will be the same as from a dipole. If you put a receiver a certain distance away and measure the strength of the signal at that receiver, it'll be exactly the same from the antenna you're talking about compared to a dipole. The ratio is 1:1, or 0 dB. And the other 0 dB gain antenna means omnidirectional. Now that is important because, let's say for example, you had to install a radio system on a mobile radio, for a mobile radio system. Okay, so we're talking about installing an antenna to communicate with people or with vehicles moving around the antenna. Okay. And somebody says to you, I've got a great antenna, ideal for what you need. It has a gain of 25 dBs. It has a gain of 25 dBs.
25 dB?
Yeah.
So that it is not diode. It looks like yeah.
Right.
DB or-
Now, remember the problem. You've got to design a system, a radio system, for mobile radio system.
So that it should be on.
Right, so if somebody says to you, here, I've got a great antenna, it's got a 25 dB gain, very cheap, it's yours for 1,000 reals.
It depends on the receiver.
Or
So
something like that.
No, it is
Could
not.
be anything.
Depends on the receiver.
Mobile, it means you have to get antenna with the omnidirection.
You should do.
So that lambda offer 16, lambda offer something with elements, or single.
Well, it doesn't matter about the type. He hasn't shown you the antenna yet. All he says is in this box, he's got an antenna with a 25 dB gain. Very cheap, 1,000 reals. Yours,
You wanted to
bargain price.
for mobile.
Are you going to buy it? That's the question I'm going to ask.
Are you gonna buy it?
Yes,
25?
25 dB gain.
No.
And you're trying to put up an antenna for a mobile communication system. Yes or no?
No, no, not wrong.
No, no.
What if he says, okay,
No, no.
500 reals?
No, no.
Still no. What if he says, okay, come on, 10 reals, take it off my hands? No, you do not buy it, because it must have a 0 dB gain to be omnidirectional. It can have slightly more than that if it's a stacked array. Slightly more. But if you're talking about a 25 dB gain, you're talking about quite a narrow,
No, omnidirectional.
reasonably narrow polar diagram, something like this. So it's not going to be suitable in any way for mobile communications, is it? As simple as that. It's not going to be suitable for mobile communications. Doesn't matter how cheap he tries to sell it you. It's useless.
What about 6 dB?
Well, you can get 6 dB gain on a stacked array. And remember what you said on Wednesday about stacked arrays. This is where you have, we have a similar arrangement up here, don't we, where we have a number of antennas under one another. And that does have a gain greater than 0, right, greater than 0. But the reason for that, though, is because it cuts out the radiation from above and below. But it's all the way round. So yes, and I think, I'm not quite sure the figure, you said 6, maybe that's where it comes from.
3 dB?
3 dBs would be, I would think, is more like the mark. Now that's not too bad, but you have to know the type of antenna in that case. But if somebody says to you 25 dBs, you're talking about a very narrow beam.
One guy mentioned from company what we purchased from I think SNDS Electronics. He said,
Electronia.
Electronics. He said we have an antenna with our system. It is 3 dB. I said, what does it mean? He said, no, because any power coming from the radio, which is inside, for example, 20
You look like 40 watts.
times 3 will be 60.
Oh no, he doesn't know what he's talking about. That's electronia, right? Yeah. That explains it.
60, so that...
Didn't you argue with him? Show him the video.
No, so that it is...
If he said what? He says it's a 3 dB, so it's 3 times the power?
Yeah, so that he said you will get 60 watts.
He obviously has no idea what he's talking about. 3 dBs is times 2, isn't it? Remember the 3.3, 10 to the power 0.3 is times 2? Always remember this figure. It's a very handy little figure to use. You'll see some antennas rated at 3 dBs. Probably there could be a stacked array or collinear. I mentioned that both words could be used. Basically, they do cut out the top and bottom powers, but they can still be omnidirectional around the antenna. So they could still work for mobile.
What's the other name?
Collinear. Did I not?
Yes,
No.
yeah, but...
Yeah.
Yes.
What كومي؟
Ask Ali, he remembers.
وش كومي؟
Not collinear, collinear.
كومي or كومي؟ Another
Collinear is another name for stacked array. Sometimes they call it a collinear array. I think I did give you both.
Omnidirectional effect, if somebody talks about omnidirection, it is zero, it should be 0.
Yes, if it's a proper omnidirectional, it means literally in all directions.
What about, we have, in the VHF,
You have a stacked array like this.
it is written, plus 3 dB.
Yes,
Plus 6, looks like what we have in trunking. Now it is 6 dB.
6 dBs. But they do that by cutting out the radiation above and below.
Yeah, the same type of
Yes, it does a similar thing, but it's still all the way around this way.
volume.
Yes, but if somebody says 25 dBs, then you know by that sort of figure, that's a much higher figure. You talk about a very narrow beam, or a much narrower beam.
So that looks like if we increase more than 0, it means to narrow it.
You're narrowing the beam some way, yes, you're cutting it out.
This is the idea.
That's exactly the idea on the antenna again. Be very careful you get a question like this in a test, particularly the radio
I
guys.
found myself it is more clever
More what? You're probably more clever than the electronia guy who said, no, I'll have to speak to that guy.
I'm surprised,
Colonia is another name for it.
Collinear. Did I not give you this yesterday, on Wednesday?
I didn't find it.
Collinear array.
Collinear array or stacked array. I used both words, didn't I,
Yes.
to describe them both. That's right, where they're up and down like this. Stacked array. It depends on the construction of the antenna, whether it's a Yagi, whether it's a stacked array, whatever it is. You don't know the diagram unless you know the details. But what you do know is that it's not omnidirectional.
Completely omni.
Completely omni, yes. Yes, that is just like a balloon around your antenna, expanding. That's 0 dB gain.
So that anything, so that there is...
Yeah, there'll be some other shape to the diagram.
What is the advantage?
Wait, you don't waste it.
The plus 3 plus 6.
Yes.
Saving energy.
Saving power, because instead of using a 200 watt transmitter, a 100 watt transmitter will do the same job. If it's a 3 dB gain, isn't it? Above, above the level of the noise.
I'm not with this.
Yes. If you use a 100 watt transmitter with an omnidirectional antenna, it's the same as using a 50 watt transmitter with an antenna of 3 decibels.
Because we double the...
Effectively doubling the power.
So that if we increase the power to 50%, so that, and we make it look like plus 3 dB.
3
The
dB.
same,
Exactly the same as 100 watt omnidirectional.
what about 6? So that it is, we need quarter. 25.
Yes, if you use 6 dBs, then of course it's a half of a half, isn't it? Or 2 times 2, so you can use 25 watts for the same power, for the same signal strength at the receiver.
And he will give me the same shape.
No, the shape must change. If you change,
Yeah, sorry, not shape. I mean the range.
it could be the same, yes, depending on what it is. Normally though, if you're going to use higher dBs than about 6 dBs, you're talking about basically point to point. For example,
The airport, they put 6 dB now until
yeah,
with the trunk.
yeah, but that's because they've reduced the above and below radiation considerably. So now they just rotate outwardly, but all the way round outwardly. But just because you transmit all the way round doesn't mean it's omnidirectional. Omnidirectional means all the way round, also at the top and the bottom. Yeah, horizontal and vertical. Omnidirectional is like a balloon. That's omnidirectional. But if you have a stacked array or collinear array, you cut out the top and the bottom radiation, and the energy that would be lost there now goes out to increase the signal in the sides, which is really how you want it. That's the most efficient for normal mobile. This array would be not very good for communicating with aircraft. Right? Because communicating with aircraft, we need radiation upward as well, don't we?
Yes.
So that wouldn't be very good for aircraft, but it would be good for communicating with people with walkie-talkies and vehicles around the airport.
So that if you use, can we use Colin array for aircraft?
But probably not.
Because up and down.
Yes, probably not. I'm not so sure they would ask a question like that in any test we do, but it should be obvious it won't.
We
Yes,
understand the concept.
yes, that's right. Because we're not concerned so much with direct communication with the aircraft. But true, that is true. You wouldn't use a collinear array like this for communicating with aircraft because of the lack of signal strength in the sky in the upward direction.
What aircraft antenna?
Oh well. Yeah. Generally, they should be omnidirectional.
What is the place with antenna?
I'm not quite sure. It depends on the design of aircraft where they put it. Depends on the design of the aircraft. Usually in the nose, somewhere. Or it could be in the tail end. I'm not quite sure. I couldn't answer that because it depends on the type of aircraft.
Mr. Tom, saying here, when the dB, when we increase the dB, that meaning is
More direct.
More direct than as well. Then that's,
Well, it makes it more efficient use of power. You get a greater signal strength at the receiver.
but you say between 6 dB, that would make the signal now.
Yes, it does. Like, for instance, it depends how the 6 dB, depends on the type of antenna that you're using. If it's a stacked array, then the reason why it's more than 0, right, 6 dBs or whatever, is because it's not wasting power up and down. But be very careful. If somebody says to you, I've got an antenna which is 25 dBs or 30 dB, then they must also be concentrating the beam this way.
Saying now, we have very high dB, that
Yeah.
meaning not only directional.
It must not be omnidirectional.
No, we cannot use it for mobile.
And that's exactly, you wouldn't use it for mobile.
But when the dB is lower, high.
Yes, I would say 6 dBs maximum.
Maximum
What do you think the gain of this antenna is going to be? Is it going to be high?
high.
Yes, it's probably going to be the highest of any antenna we're going to be considering. Very directional. If we look at the polar diagram, remember, it's essentially straight out like this. There might be a few side lobes, but essentially straight out. And the beam itself can be measured as a sort of an angle, is very narrow, a little bit like a torch beam. Now, you can expect antenna gains of this type, if we're looking at antenna gain, compared to omnidirectional, compared to all around, you can expect an antenna gain approaching perhaps 30 or 40 decibels.
40?
I was trying to look for a figure in the book I couldn't find, but I would think about that sort of figure.
30 dB.
dBs, yes. So you're talking about a very directional antenna.
So that the lower it will be less.
Yes, in fact, for the sort of communications that we use between microwave point to point, we're talking about a few milliwatts of transmitted power. all we need in order to get communication. Just a few milliwatts. Yeah.
We have 40 dB.
Because of, well, I'm putting a figure on it. I'm saying 40 dBs, but whatever it is, for these antennas we use for our dishes, on our point-to-point microwave link, we're only using a few milliwatts of transmitted power. That's all. Very small or very low power. Just sufficient. Because of the high gain of the antenna, we don't waste signals going or, radiation in other directions. So just the one direction.
Depends on the power and the gain of the antenna. Power.
It does.
The gain of the antenna is very high, the power is very low.
Yes, usually the power can be lower to give you the... That's very true.
It's
Now-
about the use the antenna.
Sorry?
The dB gain, it's depend on the use of antenna. If it's very point to point,
Yes.
To another analog signal is used as an input to a frequency division multiplexer. And in a later lesson we will discuss that. In essence, what is happening is we want to carry multiple signals, each in a different frequency band. So we multiplex them all on the same medium, and that way we can save capacity. And then a simple example of that is a cable TV system where you have different channels occupying different frequency bands. To start out then, we're going to look at digital data. And to begin, I'd want to talk about one key concept, which is the data signaling rate and the modulation rate, and the difference between the two. Data signaling rate is expressed in terms of bits per second. It's a very simple concept to understand. However, there is another concept known as modulation rate, and this is normally expressed as bauds, which stands for signal elements per second. And the reason there is a distinction here is that in the encoding process, a single bit of data can be encoded into one signal element or multiple signal elements, or on the other hand, a single signal element could correspond to multiple bits. And we will see examples of those. And to summarize that, the relationship we're talking about, shown on this slide, if one bit is equal to one signal element, then 1 bit per second is the same as 1 baud.